Good afternoon, all of you. Okay, thank you. Same to you, all of you. So don't worry. Today, mostly up to 7 p.m. I will take. Okay. So with only one break, we will take as much as possible. So all of you had dinner, lunch, not dinner. Yes. Yes, a little hang up. Zoom meeting hang up. So I don't know about network class. Okay. Okay. Let's see. The first one, speed control method, is flux control method. Let's see one by one. First one, flux control method. Yes, tomorrow also there. See, mostly tomorrow also it may not complete Sunday. Yeah, minimum at least 2 hours we will take again. Sunday we will complete DC machines. Okay. Sunday DC machines will be completed. Yes, you can listen because today is we are starting freshly, no? Speed control methods. No problem, you can listen today. Okay. Tomorrow 5:30 to 9:30. Tomorrow same as previous 5:30 to 9:30, and Sunday mostly 2 hours will be there as much as possible. Sunday we complete DC machines. Yes. Tomorrow evening we have the class. Yes, I think you will get EMF only after DC machines, I think. Or DC machines, EMF. Okay. Sunday, mostly the timing will be in the evening, 5 to 7, like that I will check. Okay, so all of you join. No, Sunday evening only because morning I have another class. Okay, see the flux control method, first one, flux control. So we will see first how to control the flux in shunt motor. After that, we go to series motor, flux control for series. Because remaining motors we don't see. Shunt motor, series motor, if you know how to control, you can control compound motors. And separately excited motor is, however, we are controlling for shunt motor, same as it is you can control for separately excited motor. That's why mainly we will see about shunt motor and series motor flux control. Considering shunt motor first. Shunt motor speed control using flux control method. Let us consider a shunt motor. Assume that initially there is no control, motor is running at its desired speed or rated speed whenever supply given. Whenever supply is given, the motor is rotating at its rated speed. No control in this. Let it is rated speed. ISH, RSH. Okay. Now this is a motor. This figure is a motor. Now we will take a drive. Drive means we will use some control in that so that it will become a drive. Now let us consider, first tell me what is the field current here. ISH equals to V by RSH. Now we need to control flux. Flux in the motor proportional to field current only, ISH. Now what is ISH? V by RSH. Now V is the supply voltage, resistance of the field winding. Now tell me, in order to change the flux in shunt motor, you need to change the field current. The field current we can change by two ways, by changing voltage or by changing resistance. So which one we have to prefer here? Okay, which one we have to prefer? Not voltage. We have to change resistance. Resistance also changing means directly we cannot change resistance. We can add some resistance externally in series with field winding. Okay, voltage is another method. Voltage control is our third method. There we do voltage control, but here as it is only flux control, voltage you should not change. That's why In order to change the field current, the only possibility is adding some resistance in series with field winding. Then the current in the motor will change. Field current will change. So flux in motor will change and speed of motor also changes. Okay. Now let us add a resistor externally in series with field winding. Adding a resistor in series with field winding. Now, what is the value of field current? Decreases because resistance added here. Therefore, ISH decrease. Whenever field current decrease, flux in motor decrease. Now, what happens to the speed of motor? Tell me. What happens to the speed of motor? Whenever we add suddenly any parameter electrically, resistance added or resistance decrease, any case, whenever we do sudden disturbance in motor, at that time the speed of motor instantly will not respond, because that is the nature of every rotating body. Sudden variation, no rotating body will takes place. That is, if you add resistance, suddenly speed will not change, because the rotor is having some inertia. Because of that, whenever we add resistor, field current will reduce, electrical quantities will change, but not mechanical quantities. Mechanical quantities will take some time to change, but anyhow under steady state. What is the speed of motor? Tell me. So we know the speed is proportional to EB by 5. Now what happens to flux in motor here? Decrease. Whenever flux in motor decrease, the speed of motor increases. So directly you can say using this relation, but definitely you may get doubt how. Whenever flux reduce, according to this equation, speed increase. But how it increases? So here there is a transient behavior. That transient behavior you should understand properly. Okay. So first of all, adding a resistor. This is motor. This is a drive. Drive it is, because there is a control in this. Changing the resistor value, external resistance, your speed of motor will change. So whenever flux decreases, you will get above rated speed. Above rated speeds only possible in this. Below rated not possible. Already we assumed it is rotating at rated previously. After adding resistor, the flux in motor reduces because field current reduces. That's why speed of motor increases. So we get above rated speed. We will get above rated speed. Below rated not possible. Below rated not possible in this. Now why below rated not possible? Because ISH already V by RSH. The only possibility is adding some resistance in series with field winding. Then when resistance added, field current decrease. Flux decrease, the speed of motor increase according to this relation. But here, you may get doubt now. What is that is, I will add a resistor in series in parallel with field winding. Then resistance decrease, field current increase, flux increase, speed of motor decrease. Is it possible? Is it possible? No. You try to add in resistor parallel. Try to add the resistor in parallel like this. Suppose it is a shunt field winding. Now try to add a resistor in parallel with this field winding. Now is the field current will increase? Tell me, because people will get doubt. Here we are adding series. So if you add in parallel, field current increases. Then if you add in parallel, is the field current increases or remains same? The field current remains same. No change in that. Why no change? If you add any number of resistors in parallel, what is the current through field winding? ISH equal to, what is the voltage at every point here? V1, V. Therefore, ISH is V by RSH. V is constant, RSH constant, field current remains same. It won't change. That's why adding a resistor in parallel is useless. That's why we never add in parallel. You don't think that like networks, overall resistance decrease, field current increase. So here field current means current in the field winding only we have to take, but not overall resistance here. Okay, so no use of adding resistor in parallel with the field winding. That's why the only chance is adding resistor in series with field. Then field current reduce, flux reduce, speed of motor increases. So above rated speeds we get. Okay. Now let's see the transient behavior, how it increases the speed. Let's see the transient behavior, how the speed increases. See, whenever we add a resistor RE, what happens to field current? Decreases. Then if field current decrease, what is the flux in motor? Decrease. Whenever flux in motor decrease, according to this relation, we are saying speed increase. But immediately no body will respond. Rotating body will not respond. But whenever flux reduce, first which one will change is back EMF. EB proportional to phi and N. Speed will not change. Whenever we added resistor, at that instant, speed same only. But what is the flux reduces? So as flux is reduced, what is the back EMF? Reduce. Whenever back EMF reduce, what is the armature current drawn by motor? Actual equation is this, V minus EB by RL. So what happens? EB decrease. Supply voltage same, resistance constant. As EB decrease, your armature current increases first. Whenever armature current increase, torque is proportional to the product of flux and current. I already explained this concept yesterday. Whenever flux reduce, you may think that flux reduce means torque reduce. But whenever flux is reducing, here IA increasing. Which effect is dominating? Yesterday I said current effect is dominating. Flux is reducing, but current effect is dominating. So overall torque is now increases. So before that, understand. First, I will take, before adding this resistance, I will assume electromagnetic torque equal to load torque. What is the meaning of this? See, every motor will rotate at one constant speed for a load. That means when a motor will rotate at constant speed, tell me, if electromagnetic torque developed and load torque both equal. Electromagnetic torque is inside the motor. Load torque is whatever the loads we connect, that will have some torque. Now, if these two are equal, then motor will rotate at one constant speed. If both are constant, motor will rotate at constant speed. If electromagnetic torque greater than load torque, what happens to, what happens now? This is called acceleration. The speed of motor increases here. If electromagnetic torque less than load torque, then what happens to speed of motor? Decelerated. Decelerated. That means speed decreases. Acceleration means speed increases. Now remember this. Remember these two statements. So initially I am assuming electromagnetic torque and load torque both are equal. Okay, initially. Now resistance added. Because of that, EB decrease, IA increase, torque also increases. Now torque increase. Which torque it is? This is electromagnetic torque. Whatever the equations we are writing, everything is electromagnetic torque relations only. Load torque we don't know. Okay. So electromagnetic torque increase. See here. Initially both are same. These two are same. Electromagnetic torque equal to load torque. Okay. Now motor speed constant. Now resistance added. Whenever resistance added, what is the electromagnetic torque? Increases. Load is remains same. Load torque is same only. Load is not changed. But electromagnetic torque is increased. Whenever electromagnetic torque increase, what is the speed of motor? Acceleration. No? If electromagnetic torque is greater than load torque, it is called acceleration. Now due to that, what happens to speed of motor now? Increase. So due to this, the speed of motor increases. Yes, speed increasing. Now whenever speed increase, observe this equation. Previously EB decreasing. Now whenever speed is increasing, the back EMF of motor now starts increasing. Now EB increase, back EMF increase. Whenever back EMF increase, what is the armature current again? Previously back EMF decrease, that's why current increase. But now as EB increasing, the armature current decreases. Whenever armature current decrease, what is electromagnetic torque also decrease. Then what is the speed of motor? Increasing or decreasing? Here you have to tell the exact answer. Now the speed of motor increases or decreases? Tell me. Speed of motor increases or decreases? Okay. Yes. Most of you saying decrease, but answer is increases. Speed of motor little increases. Now torque is decreasing. At one instant, again electromagnetic torque becomes low torque. At that time, the speed of motor become constant and rotates at same speed. Now this speed, whatever you will get, that speed is greater than the previous rated speed. That is above rated speed. Now listen here. Listen properly. This is electromagnetic torque, right hand, and left hand is load torque. Both are same initial, both equal. Now because of adding resistance, electromagnetic torque increases. Okay, electromagnetic torque increase. Due to that, what is happening? Acceleration means rotor speed increasing, back EMF increasing, IA decreasing. Now magnetic torque, because of torque increase previously, speed increasing. Okay, let previously at steady state 1000 rpm, 1000 rpm is the speed. Now electromagnetic torque greater than low torque, because of that speed increase. Whenever speed increase, back EMF increase, IA decrease, electromagnetic torque also decrease. But still, see, this is low torque, this is electromagnetic torque. Now electromagnetic torque decreasing. During that, the magnitude of electromagnetic torque greater than low torque or not? Even it is decreasing, the magnitude of electromagnetic torque is greater than low torque. That's why speeds still increase, because whenever electromagnetic torque is greater than low torque, acceleration only means speed increasing only. Okay, so because of that, speed increasing. Whenever electromagnetic torque is decreasing like that, at one instant, the electromagnetic torque will become equals to low torque. At that time, the speed become constant. Up to that, speed increasing or not? Yes. Now it is 1000 previously, steady state. But now in this case, you will get some 1200 rpm. For example, the speed of motor increases. So all of you clear? Still any doubt? Yes. Now it will become constant at a new speed. Okay. So this is the transient behavior. Generally, it is easy to say from equation. Speed inversely proportional to flux, flux decrease, speed increase. So above rated speed. That is easy, but understanding the transient behavior is important. There only the concept. Otherwise, from equation directly, everyone will say that. Okay. All of you clear? Load torque is not varying. Electromagnetic torque is varying, but the new electromagnetic torque is little increases and again comebacks. Because of that previously increase, due to that reason, the overall speed of the motor now increases. Again, it will equal to load torque, because load is fixed here. Load we did not change. Which one we changed? Electromagnetic torque we are changing in that. Okay. Yes. Yes, it is oscillating, and after that, it will reach steady state now again. Okay, right. Okay. So, what are the drawbacks of this method? Tell me. Drawbacks. drawbacks of this method. Important it is. So try to tell drawbacks here. Drawbacks. First drawback is this method is not suitable for below rated speeds because you are getting higher speeds only here. This method is not suitable for below rated speed. Below rated speed. Okay. Next, second. Tell any other drawbacks of this. Any other drawbacks? Voice Prashant, it is from only your side because no one is having. Okay. Yes. So this method is not suitable for below rated speed because if you want below rated, yes, that is what. Yes, it is not suitable for more speed control at high speed. That is also right. Very good. See, the other drawback of this method is this is not suitable for below rated. Why it is not suitable for below rated? Because for below rated, your flux in motor should increase. If you increase the flux, how can we increase the flux? Okay, anyhow, flux increased by increasing field current. Anyhow, for example, by increasing number of turns, MMF increase, field current in that is MMF increases, flux increases. Assume that flux increase. Whenever flux increase, it may reach beyond the maximum limit and it may cause saturation or not. Yes. Whenever flux increases, it may cause saturation. Okay. Now, due to that saturation, the behavior of motor will be non-linear. And the main problem here is you are increasing field current further. Whenever field current increases, the I square R loss will increase or not? Yes. Your I square R loss will be. That is field copper loss. I'm talking about field copper loss. This I square R loss increase. Then the efficiency of motor decrease. So it is not preferred to use flux control for below rated. Below rated actually not possible. And if you design any other thing also, it is not preferred because flux will reach saturation point if you increase the very high value, and which causes additional I square R loss, which reduce the efficiency of motors. And other main second drawback is this method is also not suitable for very high speeds. Very high speeds. It is suitable for above rated. Above rated means high speed, but not suitable for very high speed. Not suitable for very high speed. What is the reason? Tell, what is the reason for this? Any idea from your side? So at very high speeds also, we have some problems. What are the problems? This method is giving above rated speed, means high speeds we are getting. But it is not suitable for very high speed because at very high speed, there are some problems. The main problem is centrifugal forces. If you operate the motors at very high speed, centrifugal forces are very high. If centrifugal forces are increases, it may damage the commutator and brush assembly, and also It may damage the armature winding because of centrifugal forces. Windings may come out of the slots because of centrifugal force. And another main problem at very high speed is, if you want high speed, what should be the flux in motor? See, actually when flux reduces, speed of motor increases, inversely proportional to flux. If you want very high speed, what should be the flux? Very less. If the flux is very less, what is the main problem here? Already you know this. Tell me. If the flux in motor is very less, the problem is what? Yes, right. Yes, the main problem is armature reaction, because in order to get very high speed, you need very low amount of flux. That means that which flux it is, main flux it is. We are talking about main flux here. So whenever main flux reduces to very low value, what is the effect of armature flux on main flux? Increases. See, in armature reaction, one of the method is there. How to reduce effect of armature reaction? By creating strong main flux. But what you are doing in this method? What we are doing in this method? We are reducing the strength of main flux. We are reducing that in order to increase the speed. So whenever it is required very high speed, the flux required is very, very low. Then the effect of armature flux on main flux is very, very high. Because of that, there is heavy sparks at brushes. Heavy spark at brushes. That's why this method is not suitable for very high speeds also. Suitable for high speed, above rated speed, but not for very high speeds. Okay. So these are the drawbacks of this flux control method. Okay. Yes, easily gets distorted, it is right. So these are the drawbacks of flux control method. Now under this flux control, how this motor behaves. So previously we have seen adjustable speed drives. Now in that above rated speed, what is the type of drive? Okay, that we will prove now. What is the type of drive we get for motor? Now under this flux control, when resistance is added, what is the flux in motor? Decrease. Whenever flux is decreasing under steady state, finally what is the speed of motor? Increase. When flux decrease, speed increase, inversely related. But for the same reason, flux decrease, torque is proportional to product of flux and current. So we are considering only flux variation with respect to flux, speed increase. With respect to same flux, torque decrease. We are not considering IA here. Only we are taking IA constant. With respect to flux only we are talking. With respect to only flux. Then for the same reason, one quantity increases, other quantity decreases. Then what is the value of speed into torque? Product of the speed into torque is constant. NT constant means what is the power? 2 pi NT by 60. Power is torque omega, 2 pi NT by 60. Now this is equal to constant or not? Yes. Why? Because 2 pi by 60 anyhow constant. Now NT also we got constant with flux variation. Okay, NT is constant. Therefore, power is constant and torque is, from this relation, torque is inversely proportional to speed. Okay. So using these two variations, we draw adjustable speed drive now like this. See, it is above rated speed, torque and power variation. Let it is rated speed. This is speed, rated speed, above rated speed, below rated speed. Okay. Now above rated, We got power constant here. That's why I'm taking power is constant. Same above rated. Whenever speed increasing, what is the torque of motor? Decreasing. That is, the torque is varying like a rectangular hyperbola. This is the torque. Okay. So half of the adjustable speed drive we got in flux control, and remaining half we will see in the resistance control method. So write one statement here. Therefore, under flux control, the motor behaves as a constant power. So this is only many times repeated questions in previous examinations. Constant power drive, which method is suitable? Flux control is suitable. Okay. Under flux control, the motor behaves as constant power and variable torque drive. Variable torque drive it is. We call drive it is. Why drive? We are controlling the speed in this. That's why we call drive it is. Yes. Practicals, in this practical case, we keep the rheostat in minimum value first, then we increase. Okay. Now let's see some questions on this flux control method. Resistance adding, but small resistance we add, no? So anyhow, without adding that, how flux will change? So ultimately we need to change the speed of motor. That's why we are adding resistance. Okay. Write one question. The questions only important in the speed control method. Questions only important. Write the question. A 250 volt DC shunt motor. A 250 volt DC shunt motor has armature resistance 0.5 ohm and field resistance 250 ohms. Field resistance is 250 ohms. Full stop. It is drawing a current of 15 ampere and running at 1400 rpm. 1400 rpm. Okay. If a resistance of 250 ohms is added, a resistance of 250 ohms is added in the field winding, then the speed of motor to maintain constant power is dash. To maintain constant power is dash. See, in all these speed control methods, there will be a condition, either constant power case or constant torque case. You have to identify this one. Constant power is given or constant torque is given. So if the question is constant power question, your answer is easy one. If it is given in the question constant torque load like that, then it is little calculations increases. Okay. First, We will do both. The same problem I will do with constant power and constant torque. You will get clear that how to solve for constant power, how to solve for constant torque. So both I will do here. Okay, first consider this. First take the question, complete it, all of you. See, initially a shunt motor, 250-volt DC shunt motor. A 250-volt DC shunt motor is drawing a current of how much? 15 amperes. RSH is 250 ohm, RA is 0.5 ohm. Then what is ISH? V by RSH, 250 by 250, 1 ampere. IA will be 14 amperes. Okay. At this time, it is running at what speed? 1400 RPM. Initially given. Now calculate how much back EMF is there in this EB1. What is EB1? V minus IARA. V is 250 minus IA is 14, RA is 0.5. How much it is? 243 volts. This is EB1. First one is clear, same, whether it is power or torque. But now second case, whenever resistance added, then it will change. See, it is adding a resistance of how much in the question? If a resistance of 250 ohms is added again in the field winding, if a resistance of 250 ohms is added in the field winding. Now, what is the speed of motor under constant power? That is the important. Supply voltage is same, 250 volts. Now, what is the current? As it is constant power, power constant is product of voltage, input voltage and current is same. That's why if it is 250, 15, here also 15 only. Constant power, that's why 15 I taken. And how much resistance added? Again 250 added. Already field resistance is 250. Now 250 plus 250, 500. What is the field current now? ISH2 equal to directly V by RSH, V by total resistance. That is 250 by 500 is 1 by 2.5 amperes. Okay. Now what is the current IA? IA2. Let it is IA1. So here 15 ampere and 0.5 ampere. IA2 will be 14.5 amperes. Then calculate. We need the speed of motor N2 it is. Calculate back EMF in this condition. EB2 it is. Calculate back EMF. EB2 equals to 250 minus IA2 14.5 into RA is 0.5. So this is how much? Calculate this. So almost nearly 243 like that you get. What is back EMF? 242.75, right? 242.75 volts. This is the new back EMF. Previously 243, slightly voltage back EMF reduced. Now, how to find the speed N2? Yes, this equation. Therefore, we know N proportional to EB by 5. See, whatever we are solving now, same model for every question from now. For any speed control method, same procedure. Now, same equation we use, N2 by N1 equals to EB2 by EB1 into 5 1 by 5. Now, calculate N2 from this. N2. What is N1? N1 is 1400 into EB2 how much? 242.75. divided by EB1 how much? 243. What is the phi 1? Phi 1 proportional to ISH1. Phi 2 proportional to ISH2. What is ISH1? 1 ampere, ISH2 0.5 ampere. So ISH1 1 ampere, 0.5 ampere. Calculate this. What is the new speed of the motor? N2 equals to the new speed of motor N2 is how much? Yes, 2797, right? 2797 RPM. See, this is almost 2800 RPM. Almost double it is. Why? What is the speed previously? 1400. How much resistance added? 250 ohms added. What is the new field current? Half of the previous. If field current is half, what is the flux? Also half. If speed is inversely proportional to flux, whenever flux is reduced by half, speed will be double. Okay, that's why we are getting almost double the speed. That's why we are getting almost double the speed. Okay, 2797 RPM. Now same problem we will solve with constant torque condition. They may give anything in the question, constant power condition or constant torque condition. Based on the question we have to solve. First complete this. How IA 14? Because IA is what? This is IL. IA equals to IL minus ISH1. Apply KCL at that node. Sum of incoming currents equal to outgoing currents. Right. Now, same question with constant torque. Read the question. In the above question, find the speed of motor. Find the speed of motor for constant torque load. For constant torque load. Constant torque load. See, based on the question, we have to proceed. Okay. Constant power condition or constant torque condition. If it is constant torque, you have to take care because calculations little increases in this. Little calculations increases. See, first one is same. That is, first figure is same as it is previous. Rotating at 1400 RPM. By drawing a current of 15 amperes. Let IL 15 amperes, ISH 1, V by RSH 250 by 250, 1 ampere. ISH 1 is what? 250 by 250, 1 ampere, V by RSH. Then what is IA? Let it is IA1 equals to 15 minus 1, 14 amperes. Then how much speed it is rotating at that time? N1 equal to 1400 RPM, it is rotating. Okay. Now a resistance of 250 is added in the field winding such that condition is what in the question? Torque is the condition. That is important. Torque is the condition. 250 volts. Resistance added 250. Already 250 ohm is there. Now what is ISH2 directly? V by RSH total resistance. That is 250 by 500 is 0.5 amperes. But now you should not take the load current as 15 ampere. That is important. You should not consider the load current equal to 15 amperes because it is not constant power condition. It is a constant torque condition. That's why without considering this IL, let it is IA2. Okay. IA2 we need to calculate. How? Given the torque should be constant in both cases. Torque should be constant. Let it is T1. Let it is T2. T1 must be equals to T2. Torque is proportional to what? Product of flux and current. Phi 1 IA1 equals to phi 2 IA2. Now use this relation. Phi 1 means proportional to ISH1. That is 1. 1 into IA1 how much? 14. This is phi 2. Phi 2 means phi 2 proportional to this one, ISH2. Then what is phi 2 proportional to ISH2 means 0.5 into IA2. That IA2 we need to calculate. IA2 equals to 28 amperes. Now substitute that IA2 here, 28 amperes. See, only this calculation will increase. Calculation of IA2 will change when there is a torque condition. Okay. Now there is some back EMF induces here, EB2. Calculate how much it is. EB2 equals to 250 minus 28 into 0.5. This is 14 means 236 volts. Is it right? 236. Okay. For constant torque load condition, only current, armature current calculation will change. Now you have EB1. What is EB1 previously here? Already we have calculated EB1 equals to 250 minus 14 into 0.5. This is 243. Already we calculated previously. It is 243. Now substitute in the equation. Therefore, N2 by N1 equals to EB2 by EB1 into phi 1 by phi 2. N2 we need to calculate. N1 is how much? 1400. EB2 how much? EB2 just now we calculated here 236. EB1 is 243 into phi 1 by phi 2. Phi 1 means ISH1. Phi 2 means ISH2. 1 by 0.5. 1 by 0.5. What is the answer? For constant torque load, the speed of motor is dash. Two seven two zero. Right, very good. It is almost 2720 RPM. Now, what is the change here? If it is constant power, previous problem, what is the speed of motor you got? Almost same. Almost. That is double, almost double. But now there is some variation. Some 60, 70, 80 RPM is there. 2720. This is the new speed of motor under constant torque. Clear? In constant torque, only calculation of current IA will change. Remaining everything same procedure. Okay, completed all of this. Next question. Next question. See this one. Read the question and try this. Come back in 2 minutes. Yes, 100 ohms is right. Very good. Is 27.5 in previous. No, check it is. What is IA? See, 14 into 2, night is directly 14 into 2. That is 1 by 2 here. Cross multiply 14 into 2, 28. Okay. Now, in this question, it is same as it is previous question, but it is not mentioned in this. Is it constant power or constant torque? And it is no need to mention also, because in this question, the armature resistance is 0. The armature resistance is 0, not given. Negligible, that is. Whenever is not given, neglected. Whenever RA is 0, whether it is constant power or constant torque, there is no change. There is almost same speeds you will get in both cases. For constant power or constant torque, no variation. Same speed you will get because RA is 0 case. And one more important relation is actually how we taken previously in the previous question, flux proportional to ISH we taken. Phi 1 means ISH1, phi 2 means ISH2. But now in this question, they given one relation here, flux proportional to this relation. Now using that relation, we have to solve. A 200 volt DC shunt motor has a no load speed of 1000 RPM. No load speed of 1000. A 200 volt DC shunt motor. 200 volts is supply voltage. It is having a no load speed. Let N1 it is. How much speed it is? 1000 RPM. And armature resistance not given is 0. Field resistance given 100 ohms. Okay. Now the flux of the machine varies as this equation. Like this it is changing. First of all, from this, what is the field current? ISH1 equal to V by RSH. 200 by 100. Nothing but 2 amperes. ISH1 it is. And what is IA1? IA1. Is it given? No. Because RA is 0. Whether IA is there or not, no matter. RA is 0. What is the back EMF here? Tell me EB1 if you want to find. EB1 equals to V minus IA RA. But what is RA? 0. Then IA RA term 0. Then EB1 equals to V itself. That is 200 supply voltage. The back EMF EB1 equal to supply voltage itself. No change in that. Now, see the question. Neglect no load armature current. The resistance required in the field. We need to add some resistance to increase the no load speed to 1500 RPM. Now, same motor, we need to increase the speed to 1500 RPM by adding a resistance in the field wind. That resistance we need to calculate here. This is RE 100 ohms. RE we need to calculate. That is only the question. How much resistance we should add? For the condition given is this. This is important here. See, supply voltage same 200. Now what is ISH2? ISH2 V by RSH plus RE. V means 200, RSH is 100 plus RE. RE unknown for us. And what is the back EMF now also? Let it is speed N2. Now the back EMF is EB2. That is also same 200 volts. Why 200? RE is 0. If you take IA2 also, IA2 RE you write. That is 0 only. No? That's why back EMF is same in both cases. Back EMF same in both cases. Okay. Now substitute in the relation. What is the speed equation? Substitute. Therefore, same procedure, every problem, same procedure. N2 by N1 equals to EB2 by EB1 into phi 1 by 5. N2 we need to calculate. N1 is how much? 1000 RPM. 1000 into EB2. What is EB2, EB1? Same. That's why cancel. EB2 200, EB1 also 200. So that's why it is cancelled. Then phi 1. Flux is proportional to one relation they given. What is that relation? ISH by 1 plus 0.5 ISH. Now use this relation. If they don't give any relation, flux proportional to ISH, but they given one relation here. That's why phi 1 proportional to ISH1 divided by 1 plus 0.5 ISH1 divided by phi 2, flux proportional to same relation, ISH2 divided by 1 plus 0.5 ISH2. What is ISH1? Already we calculated 2 amperes. Substitute here. N2 equal to 1000 into ISH1 is 2 amperes. So 2 by 1 plus 0.5 into 2 is 1 by 2 into 2, 1. That is 1 plus 1 will come. Directly I am writing. 0.5 ISH1 is 2. That's why it is 1 plus 1 divided by ISH2. What is ISH2? This is 200 by 100 plus RE. 200 by 100 plus RE divided by 1 plus 0.5 into 200 by 100 plus RE. 100 plus R. In place of ISH2, I am writing this one. Clear this, all of you? First, we applied flux proportional to relation given. And in that, I am substituting the values we obtained. Okay. Now, what we get, it is N2 equals to 1000 into, this is gets cancelled because 2 by 2 it is. Now, 200 by 100 plus RE divided by 1 plus, so it will comes to numerator, 1 plus 0.5 into 200 by 100 plus R divided by 200 by 100 plus R. Now the speed N2 equals to 1000 into, so N2 is there now already. Yes, we need to increase the speed to 1500 RPM. In this question, unknown is RE. RE we need to calculate. That's why N2 is 1500. Substitute. N2 is 1500 equals to 1000 into 1 plus 1 by 2 it is. 0.5 means 1 by 2, 100 will come. So directly I am writing 100 plus RE plus 100. That is 200 plus RE divided by 200. Directly I am writing, solving this equation. And from this only unknown is RE. Calculate RE from this. The value of external resistance required. How much? Yes, 100 ohms. 100 ohms is correct. See how back EMF equals to supply voltage. So I already said the statement RA0 because that is not given in the question. Whenever not given, take RA0. Or sometimes they give armature resistance negligible. Then also RA0. If RA0, what is EB actually? V minus IA RA. If RA is 0, what is this total term? 0. EB equals to V only, supply voltage. That's why I'm writing. Okay. Yes, N2 is given. Next question. All of you completed this? Next. See this question. The field flux control method of speed control of DC shunt motor is generally used for which one of the following? Flux control method used for which one of the following? So you need this drive here. What is the drive? Power, torque, speed. Above rated speed. Flux control means above rated speed. This is rated speed, above rated speed. So above rated, what is the power we got? Constant. But what is the torque we got? Variable. So above rated speed, power is constant. Torque is variable. Now which option is satisfying? Constant HP drive below base speed, not below. Constant torque drive above rated speed. Above rated speed, power only constant, but not torque. So constant HP drive above base speed. Option D is correct. Okay. HP, constant high HP means power, mechanical power, that is. So all of you listening, no? Don't sleep. I'm getting sleep. Okay, very good. HP, actually, one HP is nothing but there are two HPs. One is BHP, one is MHP. Brake horsepower, metric horsepower. If it is brake horsepower, 746 watts. If it is metric horsepower, 735.5 watts. Okay. Brake horsepower, metric horsepower. Generally, if nothing is mentioned, we will consider brake horsepower only. Generally, brake horsepower means it is for mechanical values we take. And for electrical values, MHP we have to take. Electrical students has to take MHP. But most of the cases, we also prefer mechanical brake horsepower. Mechanical horsepower, that is brake horsepower, 746 watts. If nothing is mentioned, you take 746. Otherwise, if they mention particularly like 1 MHP, then you take 735.5. Okay. Yes. Just example I taken torque. Same question torque. So in the coming, so you will get so many questions now. There you will see torque conditions, power conditions. Again in torque condition, there are some models like if load torque is proportional to speed, if load torque is proportional to square of the speed, if load torque is proportional to cubic root of the speed. So there are some questions based on these relations. So same type of problems we also get in induction motor, same model. M means metric horsepower. B means brake horsepower. Okay. See this question. So this is not flux control, but there is a flux variation in this. It is simply the speed of the motor we have to calculate in this. First, don't fear of by looking at the length of the question. Don't fear of by looking at length. Don't decide anything just with eyesight. Okay. First, try to read with patience, not like a patient. Try to read with patience first. Nothing is there in the question. So I'm getting so much sleep because today morning I woke up at 3 o'clock with some work. From there, no sleep till now. But still, we have to take the class because to complete the syllabus in time. Okay, very good. Tomorrow is not last day. It's up to Sunday. Sunday is our last day. Yes, 5 to equal to 95% of 5, right? See, a 250-volt DC shunt motor has armature resistance 0.2 ohm, field resistance 100 ohms. When the motor is operated on no load at rated voltage, it draws a armature current. See, first draw the figure, no load condition, DC shunt motor. See, everything in DC motor speed control problems, you don't write directly. Better is draw the figure and put the data in that, calculate from there. That is easy one and you don't get any mismatches again. That's why draw the figure every time. A DC shunt motor operates on no load at rated voltage. It is drawing a armature current. Armature current they given here 5 amperes and runs at 1200. Let it is N1 equals to 1200 RP initially. Okay. Now 250 volts. There is some back EMF. Armature resistance is given 0.2. There is some back EMF at that time, EB1. How to find EB1 directly? EB1 equal to V minus IA RA. V is 250 minus IA is 5, RA is 0.2. This is 249 volts. This is EB1. This is the value of EB1. Now, when a load is coupled to motor, means load is connected, it draws a line current of 50 ampere at rated voltage with a 5% reduction in the air gap flux due to armature reaction. So due to armature reaction, demagnetizing effect, 5% reduction in flux. Voltage drop across the brushes can be taken as 1 volt per brush. And they did not mention how many brushes are there. So you take 2 brushes minimum, so 2 into 1. That is the total brush drop, the speed of the motor. Now under load condition, this is no load condition. This is no load condition. Now let us consider under no load condition. Let now under load condition. Under load, it is drawing a line current of how much? Line current 250 volts. Line current is 50 amperes. Line current they given now 50 amperes. What is the field current? Field current. Field resistance given 100 ohms. That's why if it is 100 ohms, what is ISH? V by RSH. ISH equals to 250 by 100. Nothing but 2.5 amperes. Now tell what is IA here? 50 minus 2.5. 47.5 ampere. And armature resistance is there. We have to find this speed, how much it is. This speed we need to calculate. There is some back EMF EB2 in this. What is the back EMF? EB2 equals to V minus IARA. 250 minus IA is 47.5, RA is 0.2. What is EB2? Tell me now. And minus brush drop is there. Don't forget that. Brush drop given in the question. So minus brush drop. What is the brush drop? 2 brushes. 1 volt per brush given. So taking 2 into 1, 2 volts. What is EB2? Tell me. EB2. See, no load case brush drop is negligible because no load current is very small, brush drop also very small. Only under load they are considering brush drop. That's why we taken only under load condition. Okay. 238.5, right? This is 238.5 volts. Now we have N1, EB1, N2, EB2, phi 1, phi 2. Calculate the speed N2. Calculate the speed N2 by N1 equals to EB2 by EB1 into phi 1 by phi 2. Therefore, N2 equals to, what is the N1 given? N1, 1200 RPM. No load condition, 1200 RPM into EB2. What is EB2? 238.5. EB1. What is EB1? 249. 249 into phi 1. What is the flux in both cases? Same or not? Because field current is same. But they given 5% reduction in flux under load condition. That's why no load condition flux is phi 1. This is no load. Phi 1 means no load. Phi 2 means load condition. Now, under no load, let us assume the flux is 5. What is the flux in load condition? 5% reduction due to armature reaction. So, remaining 0.955. This much. 95% is remaining. 5% reduces. Now, 5 cancel. Solve this. You will get one answer. What is the answer? Tell me. The answer is dash. What is the answer? Yes. Yes. 1210 RPM. Answer is 1210 RPM. Now, are you getting any doubt after this answer? Are you getting any doubt by looking at this answer? Tell me. Yes. Okay, breast drop we are not taking at no load condition. Why? Because under no load, current is very small, that is negligible drop. And the breast drop given in the question also for load case, not for no load case. Okay. Yes. Here you have to observe one thing is speed of the motor increases. Speed of the motor increases. Is it the right thing to increase the speed? Is it possible practically to increase this much? Is the speed increases this much? No load condition speed how much? See, no load 1200 RPM. No load condition speed is 1200. Full load condition speed is 1210 we got. Then actually is it possible practically? No. Maybe the examiner not designed properly this question. Yes, he has to design because practically it is not possible. Then how theoretically? Theoretically means values we are giving just. Why? Because he should not give 5% reduction in flux. He has to give like 2% reduction in flux. Then only it will satisfy. Because due to armature reaction, generally 2%, 3% only flux will drop, but not 5%. So in the same equation, if you put 2% reduction in flux, then how much you will get? 1200 into 238.5 divided by 249 into 5 by 2% reduction means 0.98 is there. Now calculate how much you get. Check what is the answer for 2% reduction. Answer for 2% reduction 1173. So this is the correct answer because full load speed definitely little less than no load speed. Practically that is, but theoretically they are giving any values means the creators. So now you can think how the creators are creating questions. That's why for some of the questions in examinations, no one can answer that questions. If you answer also, you will get one answer, but he will give in the key some other answer because The creator, whoever will create that in his mind, whatever he get the ideas, he will give. And whatever the answer he designed, that is only right answer. But after, if it is having so many complications, means then they will remove that type of questions also. Okay. But anyhow, here answer is 1210 only, because theoretically we got this much value. That's it. But practically I'm answering it is less than 1200. It never be more than 1200. Okay. See, okay. So here, see in this question, it draws armature current of 5 amps and runs at 1200. When a load is connected, voltage drop across the brushes can be taken as 1 volt per brush. So if you want exact answer now, in no load case also you take brush drop. Under no load also you take brush drop. It is not given clearly. Generally no load we neglect brush drop. But let us consider here and check what is the answer you get. Is it 1220? Check here. Take a brush drop in no load case also, 2 into 1. Then you will get 247 here. 247. Now substitute and check what is the answer. In place of 249, take 247. Check it now. What is the answer? For 247, the answer is how much? Yes, 1219 means nearly 1220 RPM. That means no load also we have to take. Okay, 1220 RPM. Option B only. Actually, no load we neglect. How no load and full load same brush drop? Tell me. How no load and load same brush drop? Practically, these are all not happen now, because there are some questions ambiguity will be there like this. Okay, that is gate questions. Bonus depends on that committee, whatever they decide. That is applicable for everyone. We cannot decide everything. Okay, see this question. This one. Yes, consider brush drop. If nothing is mentioned, you have to consider. Then only we are getting the 1220 now. Otherwise, if you don't consider under no load, we are getting 1210 only. Okay. Yes, it is drawing armature current of 5 amps under no load. That is a small current now when compared to 50 amperes of load current. Both options they don't give, because if both options are given, definitely we can question this one. That's why they given 1200 and one more is 1220. 1210 is not there. Okay, see this question. A 220 volt, 15 kilowatt, 1000 RPM shunt motor with armature resistance 0.25 ohm has a rated current of line current of 68. Draw the figure simultaneously. A 220 volt DC shunt motor has a rated line current, means this one, IL equals to 68 amperes, and a field current of 2.2 amperes. Okay. The change in field flux required to obtain a speed of 1600 rpm while drawing a line current and field current. So here initially speed is 1000. Now we need to increase the speed to 1600, and simultaneously they given directly currents here, line current and field current. That's why substitute it is here. Substitute here. Let it is N1 equals to 1000 rpm given, and 220 volt supply voltage. Armature resistance given 0.25 ohms. Then back EMF will be coming. EB1. What is EB1? IA1 equal to, this is 2.2. IA1 equals to 68 minus 2.2. What is 68 minus 2.2? 65.8. Calculate EB1. EB1. 220 minus IA1 65.8 into RA 0.25. What is EB1? Calculate this. EB1. EB1 203.5, right? Yes, like that. Quickly answer should be there. Very good. 203.5. Now again they given in order to obtain a speed of 1600 rpm, it is drawing a line current. So second case it is 1600 rpm is the speed. Speed N2 is 1600 rpm. Line current in this case 52.8 ampere, and field current is 1.8 ampere. Then armature current IA2 equals to 52.8 minus 1.8 will be 51 ampere. Okay. Now calculate back EMF in this condition. EB2 it is. Second case. Supply voltage no change, 220. EB2 equals to 220 minus IA2 51 into armature resistance is 0.25. 0.25. What is the EB2 value? EB2, yes, 207.25. Now we have speed and back EMF in two cases. What we have to find? Change in field. Change in field flux required to obtain a speed of 1600 rpm. Therefore, use the equation N2 by N1 equals to EB2 by EB1, 5 1 by 5. See, same procedure, complete speed control methods, but method will change, procedure will not change. Okay, substitute. N2 is 1600, N1 is 1000, EB2 how much? 207.25. 207.25. EB1 how much? 203.5 into 5 1 by 5 2. This is we have to calculate. Don't substitute now in place of 5 1 and 5 2 these values. 5 1 means proportional to this, 5 2 means proportional to this. They are proportional but not exactly same, because they are asking the change in field flux here. Now some people will think that field current values are there, directly we will compare change in field flux, but it won't give the exact value, because the flux also depends on this variation of back EMF. That's why we need to calculate 5 1 by 5 2 from this ratio only. Calculate from this. What is 5 2 by 5 1? Tell me. From this, what is 5 2 by 5 1 value? Yes, 0.636. 0.636 means the flux in second case is 63.6% of first case. How much flux is reduced just now in order to get 1600 rpm? How much flux to be reduced? Now the flux is only 63.6, means how much reduces? 36.4%. This much is reduced. The flux is reduced by 36.4%. Okay, the flux should reduce by 36.4 percentage. What is the answer? The change in field flux required to obtain a speed. So flux must be decreased to increase the speed. So decrease only correct, increase is strikeout. Decrease means 36.36. Okay. So this is the flux control for shunt motor. Now let's see flux control for series motor. How to control flux in series, because there are some special methods for series motor. Like flux control for shunt motor, however, we do same way we don't do again for series motor, because I will show you here. First completed this, all of you. See here, flux control for series motor. Starting series motor. Series motor. How to control flux in series? See, like shunt motor, let us consider a series motor first. Consider a series motor first. Applying rated voltage, drawing some current. Assume that motor is running at rated speed. Motor is running at rated speed. Okay. Now, if you want to control flux in series motor, if you add a resistor in series with field winding, what happen? If you add a resistor RE, now this is not only flux control, this is armature resistance control, because in series with armature you are adding here. In series with field winding you are adding, at the same time in series with armature. Armature resistance control will give below rated speed, but flux control will give above rated speed. Flux control will give above rated, armature resistance control will give below rated. Then can we analyze theoretically what is the resultant speed of the motor? Now can you say what is the speed? Suppose some 0.5 ohms resistor added. What is the new speed of motor? Can I decide directly? Yes. No one can decide this. No one can decide, because armature resistance control will give low speeds and field resistance control will give high speeds. Now what is the resultant speed here? Resultant speed we cannot decide. We cannot decide. That's why directly we don't add any resistor in series with field winding for series motor. To control the flux in series motor, we have some special methods. That methods only we use for series motor. Okay, write one statement here. If a resistor is added, if a resistor is added in series with field winding, in series with field winding, then it is similar to adding a resistor, in series with armature, in series with armature. Hence, the analysis of speed is difficult. The analysis of speed theoretically difficult, but practically you can get. Suppose practically you are adding in the lab itself. In the lab, you are adding some resistor. Now you can measure with tachometer. What is the resultant speed you will get? But theoretically, like this, it is difficult for us. We cannot decide what happens to the resultant speed here. Okay, the analysis of speed is difficult. Okay, due to these reasons, the methods used to control the flux in series motor. The methods used to control flux in series motor. To control flux in series motor, or there are methods, that is first one is field diverter control. Field diverter control. This is important. Second one, tapped field control. It is not important. Tapped field control method is not at all important. See, series and parallel field control. This is important. Series and parallel field control method. Okay, series and parallel field control method. Let's write one by one. First, field diverter control. First one, field diverter controller. See, already you know about field diverter concept. Diverter, already we use in compound previously. Diverter across series field winding. It is also same. Field diverter control. Field diverter control. Now let us consider a series motor first. Without any control, consider a series motor. Let this is the series motor rotating at rated speed without any control used. Without any control used. Let it is IA, RSC, RA, rotating at rated speed with some back EMF developed. Now, this question is important on field diverter and series and parallel field control. We have both constant power condition questions and torque condition questions. This is a motor, no control used in this. But now, field diverter in series, in parallel with the field winding, in parallel with field winding, a diverter is connected like this. In parallel with field winding, a diverter is connected like this. Supply voltage same, assuming constant power, that's why current drawn also same by the motor. Now a diverter is connected, variable resistance it is, diverter. Whenever diverter is connected, some current will go in the diverter resistance, and this is the current in the field winding called ISC. What is the current in field winding here? ISC equals to IA only, same. But now ISC different. That is ISC ID divided total current, and it is again IA only. So what we did in this method, some of the current is diverted in another path. Whenever current is diverted like this, what is the current through field winding? Reduces. If some current is diverted, current in field winding reduce. Whenever current in field winding reduce, what is the flux in series motor? Yes, flux in series motor also reduce because flux proportional to ISC. If ISC reduces, flux also reduces. Now what is the speed of motor? Above rated speed we get. Same as shunt motor. If flux reduces, the speed is above rated speed. But here, what is EB1 calculation? If it is EB1, V minus IA into RA plus RSC. But now EB2 it is, second case. What is the calculation of EB2? V minus IA into RA, this is RA, plus parallel combination of these two resistors. Parallel combination RD RSC by RD plus RSC. Okay. Now, in this, observe in this. This is the EB2. Calculate EB2 and you get N1 EB1, N2 EB2. N2 we need to calculate, suppose N2. We need to calculate. and EB2 you have. And here another important one is calculation of series field current. How to find that series field current? Can we apply current division rule or not? Yes. Total current is IA. See, this is the series field current. Total current is IA. Some current is going in this resistor RD. So this is RSC, field resistance. According to current division, total ISC equals to total current into opposite resistance is RD divided by RD plus RSC. Okay, this is the series field current. By current division rule, I calculated. All of you know about current division rule. Okay, this is the procedure to find back EMF in this one and field current ISC in second case. Okay, now let's see one question on this. So in this method, what we are doing, connecting a diverter across series field winding. Because of the diverter, some current is diverted in this path. Now current through field winding reduces. That's why current reduce, flux reduce, speed of the motor increase. So new speed, how much means we have to calculate all this. Then you get new speed here. Okay. Now, are you getting any doubt? Are you getting any doubt in this? Because if you don't have doubt, okay, good, that is. Unnecessarily, I should not raise the doubt. Then your doubt still increases and you will forget completely. You cannot learn anything. Any doubt? Okay, EB2 is greater, that is okay. See, what I am asking is, see, okay, observe here. This is RA here, armature resistance. In series with RA, what is the resistance here? Only RSC. But in second case, in series with RA, what is the resistance? Parallel combination of these two, RD RSC by RD plus RSC. This is there. Now there is a armature resistance control or not? In series with armature, there is a resistance variation. This is also armature resistance control, but previously I said we should not use directly resistance. But here directly we are not using, adding resistor parallelly with field winding. Now this is also changing armature resistance, but this variation is negligible variation. Why? Because the variation of flux is very high in this compared to variation of that resistance. Negligible variation it is. That's why we neglect. Here also resistance is changing. Even it is changing, we neglect it because flux change is more. Okay. So write one question. Write a question. So I will give two questions. One is with constant power, another with constant torque. So try to do both. Right. A 220 volt DC series motor drawing a current of 15 amperes and running at 1200 RPM. Armature resistance is 0.1 ohm. Series field resistance is 0.2 ohms. If a diverter of 0.3 ohms is connected, then the speed of motor under constant power load is dash. Under constant power load is dash. So this is simple one. Power load is simple. Constant power condition is simple questions. Easily you will get that. But constant torque is difficult here. For this method particularly, constant torque is important. So that question also we will solve. First complete this. A 220 volt DC series motor drawing a current of 15 amperes. IA is 15. Armature resistance 0.1. Field resistance 0.2. Calculate what is the speed here. It is initially 1200 rpm. N1 is 1200. Calculate EB1. EB1 equals to 220 minus 15 into RA plus RAC, both them 0.3. This is 4.5 volts, that is 215.5 volts. Okay, back EMF. Now what is given? If a diverter of 0.3 ohms is connected, diverter means across field winding always we connect across this. For the constant power load, that's why as it is constant power load, current drawn by motor is remains same. What is that? Previously 15, now also 15 it is. And RD how much? 0.3. RSC 0.2. Armature resistance 0.1. We have to find the speed N2 here. Speed is how much? What is EB2 now? Calculation of EB2. EB2 equals to 220 minus IA 15 into RA 0.1 plus parallel combination of this 0.2 into 0.3 divided by 0.2 plus 0.3, 0.5. See, only calculation of back EMFs and currents important in all this. What is EB2? Tell me. EB2. EB2 is 2. Yes, IA equal to ID plus ISC. 216.7, right? 216.7. Why we connect in parallel? Diverter resistance. Diverter is nothing but always parallelly only it is. It is always in parallel with field winding. That is only diverter meaning. Okay. So EB1 is 216.7 volts. EB1 is 216.7. Now substitute. Therefore, N2 by N1 equals to EB2 by EB1 into phi 1 by phi 2. But observe this one. Phi 1 proportional to series motor, flux always proportional to IA only. Flux proportional to IA here. But in the second figure, flux proportional to ISC or not. This is ID. This current is ISC. Flux proportional to ISC. In the second case, phi 2 proportional to ISC. Phi 1 proportional to IA. How to find that ISC? Calculate ISC first. Current division rule. ISC. Total current 15. Opposite arm resistance. Opposite resistance 0.3 divided by total resistance 0.3 plus 0.2, 0.5. How much it is? 3 by 5. Nothing but 5 is 9 ampere. ISC is 9 ampere. Current division rule applied. ISC is 9 ampere. Now substitute here. N2 we need to calculate. N1 is 1200 rpm. EB2 is 216.7 volts. EB1 is 215.5 volts. Phi 1 proportional to IA, that is 15. Phi 2 proportional to ISC, that is 9 ampere. So 15 by 9. What is the answer? Speed N2 how much? N2 2011, right? Speed N2 is 2011 rpm. This is the new speed of motor under this condition. Now I will give you a constant torque condition. You only try this first, whether you will get or not. Okay. Write the question. Constant torque condition now. It is constant power, easy one. But constant torque is important model in this. All of you completed this? So don't sleep. Okay, don't sleep. Just wait for 2 days. I won't come in front of you. Write the question. A 500-volt series motor has armature resistance equals to zero point 0.4 ohms, RSC equals to zero point 0.3 ohms. It is drawing a current of of 100 amps at 600 rpm. If a diverter of if a diverter of 0.6 ohms is connected in the field winding, means diverter always parallel only. In the field winding means it is not in series. Diverter means parallel with field winding always. Okay, in the field winding, then speed of motor to maintain constant torque load constant torque load is dash. So try this. I will give 2-3 minutes time. Try this. Oh, Pragati 2021, did you return gate? I think for your batch in last January, it is gate taken transformers. No? Okay, so at least try this year again. Try to get top 100. Okay, 613, 420. Yes, yes. Saumitri, right? Palwar, sorry. Yes. Yes, those who got 729 RPM is the right answer. 729 RPM is correct. 729 RPM is right. See, simple, same procedure, but only calculation of current based on the torque condition it is. Okay. Now, see, initially the motor is running at 600 RPM, drawing a current 100 amps. Take that figure. Series motor running at uh, supply voltage is 500 volts. 500 volt supply voltage. Current IA1 let 100 amps. Armature resistance is RA is 0.4, RSC 0.3, and it is running at 600 RPM in this. Calculate back EMF at that time, EB1. EB1 equals to 500 minus 100 into RA plus RSC 0.7. This is 430 volts. Okay, this is first case. Now we are adding a diverter of 0.6 ohms. Diverter of 0.6 ohms is connected like this. A diverter of 0.6 ohms is connected. In this way. If a diverter of 0.6 ohms is connected under constant torque load, diverter of RD equals to 0.6, RSC 0.3, and armature resistance same 0.4. What is the speed N2? This is we need to calculate. EB2 you can find, but here current is not same as previous. You have to take it is IA2. It is not constant power. If it is constant power, voltage current same you have to take, but now it is constant torque. Okay, that's why IA2 same current will not come. IA2, but IA2 unknown for us. So find IA2 using the torque condition. What is the torque condition? T1, torque in two cases must be same. T1 equals to T2. T1 means what is the torque proportional to phi 1 IA1, phi IA. T2 means phi 2 IA2. In the initial case, flux phi 1 proportional to IA1 only. But in the second case, here, flux proportional to ISC it is. This is ID. ID. So flux proportional to ISC. Therefore, phi 1 proportional to IA1 only, IA1, IA1, IA1 square, phi 2 proportional to ISC into IA2. IA1 we have 100 square. And how to write ISC? Current division rule. What is ISC? Current division rule. ISC equals to IA2 into opposite resistance 0.6 divided by total resistance 0.9. So 2 by 3 will come. 2 by 3 IA2. ISC is 2 by 3 IA2. ISE is 2 by 3 IA2. Substituting here 2 by 3 IA2 into IA2 into IA2. Now only unknown is IA2 in this. Calculate IA2 from this. How much IA2 we get? IA2 how much? 122.47, right? 122.47 amperes. This is IA2. New current it is. For constant torque to maintain this much current it will draw. This is IA2. Now if it is IA2, ISC how much? 2 by 3 IA2, no? ISC means 2 by 3 IA2. What is the 2 by 3 IA2? 2 by 3 into 122.47. How much it is? 80. This is yes, 81.6 amperes. This is ISC now. What is EB2 from the second diagram? EB2 equals to, from the second diagram, EB2 equals to V minus total drops. V is 500 volts minus IA2. IA2 is 122.47 into RA. What is RA? 0.4 plus parallel combination of RD RS 0.3, 0.6. 0.3 into 0.6 divided by 0.3 plus 0.6 is 0.9. Solve this EB2, you will get the EB2 value. EB2 426.5. 426.5. This is EB2. Okay. Now same as previous calculations. N2 by N1 equals to EB2 by EB1 into phi1 by phi2. Calculate N2. N2. N1 is what? 600. EB2 is EB2 to 426.5. EB1 470, no? 430. EB1 is 430 into phi1. Phi1 proportional to IA1. What is IA1? 100. Phi2 proportional to ISC. Phi2 proportional to ISC 81.6. Then the speed you will get 729 RPM. This is the new speed of motor. Okay. So this is field diverter model problems. Calculation of current important in torque conditions, constant torque condition. Okay, so take a break. So after break we see the remaining. Mostly today we'll try to complete speed control methods. Okay, take a break. See, for a given torque, reducing the diverter resistance of a DC series motor. So what happens now? For a given torque means torque constant. Torque is constant. Reducing the diverter resistance. Okay, see here. Given torque means torque must be constant. Now, what they are saying, for a given torque, reducing diverter resistance. Torque must be constant. Torque is proportional to product of flux and current. Okay. So for a given torque, reducing diverter resistance. When RD reduce, what is ID? Increase. Then what is ISC? ISC decrease. If RD reduce, diverter resistance reduce means current through that increases. So ID increase. ISC reduce. Whenever ISC reduce, what is the flux? Reduce. Whenever flux reduce, what is the speed of motor? Increases. Speed of motor increase. But what is the current? Armature current is dash. Speed reduce, but what is the armature current here? Tell me. Speed of motor increases. What is the armature current? Because torque should be same. What happens here? Flux is reducing. Flux is reducing now. So in order to maintain same torque, what should be the current? Increase. So flux is reducing. So due to that speed increases and it will draw more armature current from supply. It will draw more armature current from supply. So answer is increases its speed. Increases its speed, demanding more armature current. Option B is correct. Okay. Increases its speed, demands more armature current because torque should be same again. That is the condition here. Torque should be same. For a given torque means torque must be constant in this. Okay. Next. So this type of questions little confuse you during the examination and you should take care from the options given. What is the answer for this? What is the increase in torque expressed as a percentage of initial torque if the current drawn by a DC series motor is increases from 10 to 12 amperes? Means in a series motor, torque is proportional to Ia square. Okay. What is the torque initially? Current is initially 10 amperes. When Ia is 10 ampere, what is the torque? Ia square. 10 square means 100. If Ia is 12 amperes, what is the torque now? Ia square. 12 square. 12 square is nothing but 144. So initial torque is like 100, proportional to 100, let 100 Newton meters. Now what is the torque? 144 Newton meters. So what is the percentage of increase in torque? 100 initially, now 44 increase, nothing but directly 44% increases. Okay. Next, second method for series motor is IA equal to ID plus ISC. Yes, if ISC decrease, ID increase means here torque condition. Who said IA constant? We should not take IA constant directly. Power means IA constant, but torque condition here. That's why IA will change. Okay, ID increase, ISC decrease, and in that itself, IA also increasing. IA should increase because here we don't have values to say directly because torque condition IA is not constant. Next, second method in the series motor is tapped field control method. Tapped field control method. Tapped field control. In the name itself, tapped field. Now let us consider a series motor first. Consider a series motor. Consider a series motor. Let rated voltage is applied. Motor is running at rated speed. Just without any control in this. At that time, current is IA. Total turns is N. MMF produced is NIA. Now motor is rotating at rated speed. This is a motor. Now drive means control. Now here field winding we will tap. We will provide tappings to the field winding like this. Let tapping 1. Let it is tapping 1. Let it is tapping 2. Let it is tapping 3. It is tapping 1, tapping 2, tapping 3. And these tapping positions we operate with a movable switch here. These tapping positions we operate with a movable switch. This switch is movable. You can move this. You can move the switch here to tapping 1, tapping 2, tapping 3. So here we give supply voltage. Supply plus minus. And if the switch is closed at tapping 1, if the switch is closed at tapping 1 here, now current will flow from this point through all the turns. Current is flowing in all the turns here. So at tapping 1, whatever MMF is there, let it is IA. Whatever MMF is there, N into IA, it is same as previous NIA or not? Yes. That means, is there any change in the MMF? No change. Flux also no change. So with respect to tapping 1, the speed of the motor, let N1, is same as the previous rated speed. That one, first one. First one is rated speed. Now at tapping 1, speed is remains same because no change in the flux. Now observe, suppose the switch is closed to tapping 2. The switch is closed to tapping 2 now. Tapping 2. Switch is connected to tapping 2. Now current IA will flow from here in this direction. This is the current because current cannot flow in this side because open circuit now it is. That's why current will flow from this turns to all the turns. Means how many turns current is flowing? Less number of turns. Therefore, at tapping 2, what is the speed of motor? MMF is less. Tapping 2, MMF is less. MMF is less at tapping 2. If MMF reduce, flux also reduce. Whenever flux reduce, what is the speed of motor? Let N2 greater than N1. N2 is greater than N1 because MMF reduces, flux reduce, speed increases. Next, let us close the switch at tapping 3. At tapping 3, observe, current is flowing from here. Current is flowing from this point only in this direction. How many turns current is flowing now? Still very less. The current is flowing still very less number of turns. So with respect to tapping position, the current flowing in the number of turns is changing. That's why MMF will change. MMF at tapping 3 is still very less. Due to that, the speed N3 you get is greater than speed N2. Like that, tapping 1, for example, speed at tapping 1 is 1000. Tapping 2 speed will be 1200. Now tapping 3 speed is, let's say, 1400. Like that, your speed will increase step by step with tapping changing. This is called tapped field control. But what is the drawback of this method? What is the drawback? Suppose I need a speed of 1250. Can I get in this method? No. I need a speed of 1300. Can I get in this method? No, not possible. So whatever the speed we want, we don't get in this method. This method will give fixed speeds because the tapping positions, whatever we placed, they are fixed tapping positions. It is not possible to get variable speed here. But in the previous diverter control, when RD value changes 0.1, 0.11, 0.12, 0.13 like that, different speeds you get. But here it is not possible. Now you should get one doubt. What is that? In this field winding also, you don't place fixed tapping. Let us place a tapping point just like auto transformer, movable tapping point. Movable. Point is moving smoothly, moving. 1 turn. Now, can we use that movable tapping point just like transformer, auto transformer? Can we place movable tapping point in this? No. You cannot place movable point. Why? Because where these field windings are located? On the pole core. On the pole core, it is located. And how many turns are there in series field? Less number of turns or more number of turns? Less number of turns. That is, you can count also 6 turns, 7 turns like that. If it is less number of turns, if you place a winding also, how much thickness you will get here? How much width of the winding you get? Very, very less. Now here, where you will move the point again? Where you can move the tapping point? That much space not available first. Then you cannot place a movable point. Suppose you placed also. There is a main problem. Another problem is when you place a movable point here, whenever you move the point, during that there is a heavy spark between two turns. Heavy spark. Why heavy spark? Because what is the current flowing in the series field? High current. That is armature current. Because of that armature current, when you move the point, when you change the tapping point, then there is a heavy spark. Because of the spark, sometimes windings also will bounce. That's why we never preferred movable tapping point on this. Only fixed points. And that tapping points is done inside the machine and taken outside to the terminal box. In the terminal box, we will change the tapping position. That's it. Internally, we cannot change. During the manufacturing stage itself, tapping should provided inside. Okay. This method will give only fixed speeds, but not smooth variation of speed control because it is not possible to place a movable tapping point. It is not possible to place a movable tapping point. Motor not short circuit. If you place the tapping point at the last also, there is no use. Means flux will not produce. Flux is very, very less. Then it is dangerous high speed, just like shunt motor. That's why at least some turns we allow, not completely up to end of this. Okay. Tapping we provide at least some number of turns. Up to last we cannot. Okay. So anyhow, from this method, you don't get any question. If you get question also objective type, like at which tapping point on the field winding you will get high speed? Tapping near to armature, tapping near to supply voltage. Tell me. Tapping 1 near to supply voltage. Tapping 3 near to armature it is. So where you are getting high speed, tapping 3 you are getting high speed. So wherever the tapping is nearer to armature, that point will give highest speed in that. Okay, remember this point. So more than that, no numerical questions on this method. Next, series and parallel field control. Third one, series. This is important for ESC particularly. Series and parallel field control. Field control method. So what is the name? What is the meaning of this method first? Series and parallel field control. Series and parallel field control means what series, what parallel? Field winding. Series motor means field winding must be in series with armature. Series only. Then what is again series and parallel field control? Yes. So what it is observe here. Let us consider a series motor first. Consider a series motor applying rated voltage, armature current. Let there are some number of turns in this N, and motor is rotating at rated speed at that time. Now what we do in this method is whatever the number of turns is there in the field winding, suppose 10 turns or any number of turns N, that much number of turns N, we will divide into some equal parts, maybe 2 parts, 3 parts, 4, 5, 6, and so on, any number of parts. Now I will divide example 2 parts, 2 equal parts. That means I will divide the complete field winding into 2 halves. Then how many turns will be there in each half? N by 2 will be there. Now I will draw here the 2 equal parts. I will connect in series again. This is called series field control. This is called series field control it is. But no use of that series field control. So why it is we observe here. See, N by 2, N by 2. 2 parts, both I connected in series. Assuming constant power, that's why same current will flow. Now we have to find what is the speed in this series connection. Suppose the same 2 parts of the winding I will connect in parallel like this. N by 2, N by 2, both I connected in parallel. Both I connected in parallel. This is IA, N by 2, N by 2. Same, both I connected in parallel. What is the current now? Equally divides because number of turns are half. Current equally divides. IA by 2, IA by 2. This is called parallel field control. Second, this third figure is parallel field control. This is series field control. Now, what is series and parallel field control? Series and parallel is possible with minimum 3 equal parts or 4 equal parts. So, for example, let us divide the series field winding into 4 parts. 4 equal parts means N by 4, N by 4, N by 4, N by 4 like this. This is connected in series with armature. This is the meaning of series and parallel field control. This is the example for series and parallel field control. Means total 4 parts, N by 4, N by 4, N by 4, N by 4. Out of that 4 parts, 2 are connected in series, 2 are connected in parallel. This is the combination of both series and parallel combination. Here, second one only series, and this one only parallel. Okay, this one is only parallel, and this one is series and parallel field control. Like that, you can make any number of parts, 10 parts in that, 2 in series, 8 in parallel, 3 in series, 7 in parallel, 4 in series, 6 in parallel. Like that, you can do any number of combinations. You will get different speeds. But what is the problem of this? What is problem of this method? Problem. The main problem of this method is this method practically difficult. Why practically? Can you open the field winding? Can you cut the field winding into number of parts? We cannot do all this. Practically, no one can do all this. Can you open the machine and can you cut the field winding into number of pieces? Can you attach in series and parallel? No. These are all practically not possible. But when it is possible is during manufacturing conditions. During manufacturing stage itself, if it is provided for some combinations, 2 in series, 2 in parallel, 3 in series, 2 in parallel, like that, some combinations provided inside and given outside in the terminal box. Now in the terminal box, by changing the connections, you can operate it, but directly you cannot open the field winding and you cannot fit. Okay, these are all pre-arranged connections. But first one, field diverter is not pre-arranged. You can connect a diverter externally. You can connect a diverter. You can change the diverter value. Speed of motor will change. But tapped field control and series and parallel field control are the pre-arranged connections. Otherwise, we cannot do this. Okay. So anyhow, this case we will do with one example problem. Just remember this. Observe here. Initially, we taken a motor. What is the MMF produced in this case? MMF N into IA. Okay, MMF I will indicate as ampere turns AT. Ampere turns in this connection is NIA. That's why speed is rated speed assumed. Now second connection, series field control. Now the two parts of field winding I connect in series only. Then what is the current flowing in these two parts? Same current will flow IA. Now calculate ampere turns in series connection. Try to find ampere turns in this. Ampere turns means total, any number of parts are there, you add all the ampere turns. First NIA by 2, NIA by 2 plus this one also NIA by 2, NIA by 2, NIA by 2, NIA. Means what is the MMF previously? NIA. Now also what is MMF? NIA. Is there any change in MMF? No. That's why flux also will not change. Then what is the speed in series? Same as it is rated speed. No change in the speed because speed inversely proportional to flux. And we are neglecting that EB here because EB equals to V minus IA RA plus RSC. That RA plus RSC drop I am neglecting, small drop, neglecting in this method. That's why directly inversely proportional to flux, inversely proportional to ampere turns. Okay, inversely proportional to AD. Here, if ampere turns change, speed will change. Now observe this parallel connection. Parallel connection it is. Current equally divides. Find the total ampere turns in parallel connection. Ampere turns. For this one, NIA by 4. NIA by 4 plus for this one here NIA by 4 again. NIA by 4. What is the total? 2 NIA by 4, nothing but NIA by 2 will come. Now MMF is half or not? Yes. In parallel connection, MMF is half compared to previous connection. If MMF is half, what is the flux also? Proportional to MMF, half. Then what is the speed? Speed inversely proportional to flux or inversely proportional to ampere turns. If ampere turns is half, your speed is double. Okay, so parallel connection speed will change, but series connection, if you connect infinite parts also series, your speed will not change. Parallel only important here, and combination will change again the speed. So that we see one question also with this. First take the figures. So right here one statement. In this method, the field winding is divided into, in this method, the field winding is divided into n equal parts, and connected in series and parallel. in series and parallel combination, in series and parallel combinations, which will change, which will change mmf and flux in motor, mmf and flux in motors. Okay, but it is difficult practically. We cannot do every time, but these are all pre-arranged. During the construction itself we have to arrange this. Now, so I'm writing speed is inversely proportional to flux. Speed is inversely proportional to flux, which is inversely proportional to mmf, nothing but ampere turns. So using this relation, speed in parallel connection to the speed in series connection equals to ampere turns in series connection to the ampere turns in parallel connection. What is the speed in parallel? Speed in series is rated speed into ampere turns in series NIA. Ampere turns in parallel NIA by 2. NIA cancel. This is 2 times of the rated speed. Okay. If the field winding made 2 equal parts, your speed is double. If the field winding is made 3 equal parts and connected in parallel, your speed is triple. Like that, if you made n number of parts, n times your speed increase. Okay. For parallel connection, it is n times. Let's see one question. Write the question. A 220-volt DC series motor is running at 1000 rpm. 1000 rpm. If the field winding is made 4 equal parts, if the field winding is made into 4 equal parts, 4 equal parts in which 2 are connected in series, 2 are connected in series and 2 are connected in parallel, 2 are connected in parallel, then the speed of motor under constant power is dash. Under constant power is dash. These are the options. 1000 rpm, 1333 rpm, 1666 rpm, 2000 rpm. What is the answer? Yes, answer for this question is option B is correct. 1333 rpm. See, what you have to do is first draw the connection and then calculate the ampere turn in that or mmf in that, and then compare the two cases. You will get the answer. That is, let us consider a series motor first. Initially, the series motor is running at 1000 rpm. Initially, 220 volts. The motor is running at 1000 rpm. This is 1000. Let number of turns is total n. Speed is initially 1000. What is the ampere turns in this connection? 81 equals to NIA. Now what is the question? The field winding is made into 4 equal parts, in which 2 connected in series, 2 connected in parallel, like this. Like this it is connected. What is the speed N2? How many turns are there in each? 4 equal parts. That's why n by 4. If it is 40 turns, 4 equal parts means each one 10 turns. That is nothing but 40 by 4. Like that, n by 4 it is. N by 4. As it is constant power, what is the current drawn by motor? Same as previous. IA only. If it is IA, here also IA. Now what is the current division? Equal turns. That's why half of equally divides. IA by 2, IA by 2. Now calculate the total ampere turns in the second connection. That is only important. Total ampere turns in second connection. This one. For this one, n IA by 8. See, n by 4 into IA by 2. Ampere turns. N IA by 8. Plus, for this one also, n IA by 8. Next, n IA by 4 it is. And one more also, n IA by 4. So add all these 4 and you will get total 3 by 4 NIA, this value. Okay. Total ampere turns you will get 3 by 4 NIA. What is 81? NIA. Therefore, N2 by N1 equals to inversely proportional to ampere turns. So using this N2 by N1, I am writing 81 by 82. Therefore, N2 equals to N1 is 1000 into 81 is NIA divided by 82 is 3 by 4 NIA. Now in this NIA cancel, N2 equal to 1000 into 4 by 3. This is 1333 RPM. Okay. Same procedure for any question. You have to find total ampere turns in that and compare with previous case. Clear? Oh, MMF is different, current is different, no? Because in all parts, current is not same. See, if you take this figure, what is the current in these parts? IA. What is the current in same N by 4 here? IA by 2. That's why current only we should not take. Total MMF we have to take. Next question. Right. In the above question, write the question. In the above question, if all 4 parts are connected in series, if all the 4 parts are connected in series, then speed of motor is dash. Speed of motor is dash. What is the answer? If all 4 connected in series only, yes, obviously same speed. If you connect any number of parts in series, your speed will not change. 1000 only. Whatever is there previous, same it is. No change. Now again, one more question. In the above question, if all 4 parts are connected in parallel, if all 4 parts are connected in parallel, then speed of motor is dash. Speed of motor is dash. What is the answer? Yes, very good. 4,000 because 4 parts na it is. For 2 parts, double, 3 parts, triple, like that. If it is 4 equal parts, the speed will be 4,000. So if you want, suppose in between somewhere, you need to calculate. So how to arrange the winding such that to get 3,000 RPM. Okay, like that we have to calculate. Or 3,500 required. How to arrange the winding? You have to calculate. Okay, then arrange, you will get the required speed. But this is difficult one. Making the connections is little complex. It is difficult. Now, this is constant power. Whatever we have seen up to now. Let's see one question on constant torque. Right. A 220 volt DC series motor running at 1000 RPM. 1000 RPM. If the field winding divided into two equal parts. Two equal parts in which two equal parts and connected in parallel because only two night is and connected in parallel. Stop. The speed of motor under constant torque load condition is dash. The speed of motor under constant torque load is dash. Constant torque load is dash. These are the options. 1000 RPM, 1414 RPM, 1617 RPM, 2000 RPM. What is the answer? Answer is dash. What is the answer? Okay. So randomly saying 1617, 2000. Okay. So you have to answer something, then only interest. Okay. Anyhow, if it is a constant power, what is the answer? 2000. If it is constant power, answer is 2000. But if it is constant torque, answer is not 2000. Answer is 1414 RPM. 1414. See how? Same procedure again. Do it. Same procedure. Do it again. That is, consider a series motor first. It is rotating at 1000 RPM. Same procedure, but here current you should take different, not same current, because voltage anyhow constant, current is different because it is a constant torque. That's why speed n1 is 1000 rpm given. Let the total turns in the winding n. Now what we did, field winding divided into two equal parts and both connected in parallel like this, n by 2, n by 2, both are connected in parallel, n by 2, n by 2. And what is the current? Let ia2, because current is different here. ia2, how it divides? Equally divides. ia2 by 2, ia2 by 2 equally divides. Okay. Now what is the speed n2? Same procedure, but here 81 how much? N ia1. 82 how much? 82. N ia2 by 4, N ia2 by 4, both I'm adding at a time. N ia2 by 4 plus N ia2 by 4, nothing but 2 N ia2 by 4. It will be N ia2 by 2. 82 it is. Now we need the relation between that ia1 ia2, because as condition is torque T1 equals to T2. Use this. Phi 1 ia1 equals to phi 2 ia2. Flux proportional to mmf, that is at1 ia1 equals to at2 ia2. at1 ia1 equals to at2 ia2. Now from this, at1 means what? This is n ia1 into ia1. at2 is what? N ia2 by 2 into ia2. Okay, so just I written this equation here. Now in that we get one relation, n cancel, ia1 square equals to ia2 square divided by 2. From this, ia1 equals to ia2 by root 2. This is the relation. Suppose if they given ia1 10 amperes, ia2 you can find from this. Here it is not given, that is a relation. Therefore, complete here up to this. Therefore, n2 by n1 equals to speed inversely proportional to ampere turns, mmf. That's relation I'm writing, 81 by 82. What is n2 equals to? N1 is 1000 rpm, 81 means NIA1, 82 means NIA2 by 2. Now substituting here, n cancel. This is 2 into 1000 into IA1 by IA2. What is IA1? Or IA2 is what? Root 2 IA1. IA2 is root 2 IA1. IA1 cancel now. This is root 2 cancel. 1000 root 2. Nothing but 1414 RPM. That is the speed. 1414 RPM. Okay. Make a note here. Note. Yes. So mostly before 7 itself we leave. Okay. So I'm not comfortable today. Okay. See, make a note. So the same above question without solving also you can answer with this note pointer. That is, write the note. If field winding is divided into, if field winding is divided into small n equal parts, small n equal parts, and all are connected in parallel, all are connected in parallel, connected in parallel, then first case. So we have two cases, constant power, constant torque. Then first one is for constant power, for constant power, the speed of motor is n2 equal to small n into n1. Okay. Okay. For constant torque, directly use that relation. Root n. So if it is two parts, root 2 into that speed, 1000, or previous one, 1000 root 2 is the answer. If it is four parts, root 4 nothing but 2. That is speed will be double. That is for constant power and constant torque. Directly you can use that relations. Okay. Series, no, not required. Series, whether it is power or torque, anything, answer is same, no change in the speed. Series is waste. Only parallel and combination of series parallel is we get the speed. Okay. So with this, flux control is over. Next. Next, armature resistance control. Next method, second method is armature resistance control method. Armature resistance control method. Armature resistance control method. Now, this method is best suited for which motor? Best suitable. Best suitable means there are three methods now: flux control, armature resistance control, voltage control. Best suitable method means, suppose when you change flux, the remaining two should not change. The remaining two should not change. That is the purely flux control. Or when you change resistance, remaining two should not change. That is purely resistance control, like that. For which motors it is best suitable? Yes, shunt motor and separately excited motor. When you add armature resistance, external resistance in series with armature, there is no change in flux and no change in voltages. Supply voltage same, flux same. But in series motor, it will change. How? In case of series motor, if you add a resistor in series with armature, current will change. When current changes, flux in motor also change. That's why it is difficult for us to analyze what happens for series motor. But practically, if you are in lab, you can add some resistor in series with series motor also, in series with armature for series motor also. There you can observe by tachometer directly what is the speed of motor. Okay, that's why here we will consider shunt motor for armature resistance control. Considering a shunt motor, before any control in this, consider a shunt motor. Let rated voltage is applied. Current is IL, IA, ISH. Armature resistance RA, RSH. Back EMF EB. Let us assume initially this motor is running at rated speed. This motor is running at rated speed. Okay. Now in this method, we will add some resistance in series with armature externally. Internally, we cannot add. Externally, we can add some resistance in series with this. Okay. Now let us add some resistance in series with armature. What is the flux in shunt motor? Constant or not here? Yes, constant. ISH equals to V by RSH. We are not changing supply voltage. RSH anyhow will not change. Constant. Flux is constant. Now only resistance control we are doing. Voltage also constant, flux also constant. Voltage and flux. Only resistance control. Okay. Now adding a resistor in series with armature. Adding a resistor in series with armature. Now whenever resistance added, what is the speed of motor? What is the speed of motor? Is it changing instantly? No. At any time, if you change instantly any electrical parameter, the mechanical speed will not disturb suddenly. At that instant, it is same only. After that, what happened? That we need to consider. See, IL, ISH, no change. See, whenever resistance is added, what is the speed of the motor? That we need to calculate. See, we know the relation. Speed is proportional to EB by phi. EB by phi. What is EB? Flux is not changing. Flux constant here. That's why remove the flux. Now only EB is varying. So EB proportional to V minus IA into RA. But in this method, we are adding resistance in series with armature. Whenever resistance added, what is the resistance drop here increases. Then what is V minus IRA decreases. The speed of motor decrease. So we get below rated speed. In armature resistance control, we will get only below rated speed, but not above rated. With resistance RA, it is rated speed previously. After adding this resistance, speed decreases. So that is below rated speed we get. Below rated speed. Now let's see the transient behavior here, how it will change. Transient behavior. See the transient behavior. Whenever, first I will take steady state. Before changing steady state, electromagnetic torque equal to load torque. Then motor is rotating at a constant speed of rated speed. Okay, this is steady state initial. Now adding a resistor in series with armature. When resistance added, what happens? What is the armature current? IA equals to V minus EV by RA plus RE. Resistance added. Whenever resistance added, what is the current? Because supply voltage constant, at that instant EB also constant. Why? EB proportional to N phi. In this method, we are not changing flux, constant. Speed at that instant, same only, because suddenly speed will not change. When resistance added, the speed also no change. That is, these two are same. That's why EB constant only, no change in that. That's why denominator part only increase. Then what is the current IA? Decrease. Whenever current decrease, torque proportional to flux IA. As IA decrease, flux constant, torque also decrease. Now which torque it is? Electromagnetic torque. Whenever torque decrease, now previously both equal. Now electromagnetic torque only decrease, load is remains same. Then electromagnetic torque is less than load torque. Now what happens because of this? Deceleration of rotor takes place. Deceleration means rotor speed decreases. Whenever rotor speed is decreasing, what is the back EMF now? Whenever speed starts decrease, EB also decrease. When EB decrease, what is IA now? V minus EB by RA plus R. Previously, after adding resistance, denominator increase, current decrease. But now EV decrease. Then what is V minus EB? Increase. So current little increases. Whenever current little increase, what is the torque now? The electromagnetic torque again increase. Whenever torque increase, what is the speed here? Tell what is the speed? Increases or continue decreases? Increases or continuously decreases? Previously also I asked the same like this. Now what is that speed? As torque is increasing now, what happens to speed? Decreases or increases? Previously also same as it is I asked. So here the speed decrease. Why decrease? Still electromagnetic torque less than load torque. Still it is not arrived. Both is not equal. That's why it is. See again. This is electromagnetic torque. This is load torque. Steady state both equal. Steady state both equal. Okay. Now after adding external resistance, IA decrease, electromagnetic torque decrease. Now electromagnetic torque is less than load torque. Because of that, rotor speed is what? Decreases. Whenever speed decrease, EB decreasing, observe the equations, EB decreasing, IA increasing. When IA increase, again torque increase. Torque increasing means still it is less than load torque or not? Yes. That's why rotor speed still continue to decrease. At one instant like that, whenever it is happening, electromagnetic torque will come again equals to load torque. Then the speed become constant. Speed decrease, decrease, decrease. At one time, speed constant because both equal again. Understanding? Both the torques are equal. That's why speed now becomes constant. But finally, previously let 1000 RPM. Now the speed of this motor will be less than that. Let some n equal to some 900 RPM. Below rated speed we get. Okay, clear all of you this one? Load torque same only. Load torque will not change. Load is fixed one. That's why load torque is not changing. See again, electromagnetic torque, load torque, both are equal. Okay, this is load torque, this is electromagnetic torque, both equal before disturbance, steady state. 1000 RPM it is rotating. After adding external resistance, what is the electromagnetic torque? Decreases. Whenever electromagnetic torque is less than load torque, what is the position of the rotor? Decelerate. Means speed decreases now. Rotor speed decreasing 1000 to 950, like that. It is decreasing. Whenever speed decreasing, again observe the equation. When speed decrease, back EMF decrease. Now IA increase. Whenever IA increase, electromagnetic torque again increasing, increasing, increasing. But still it is less than load torque only. That's why the rotor speed continue to decrease like that only. 950, 940 like that. Whenever this electromagnetic torque again equals to load torque, whatever the speed decreasing previously, that will reach one speed and constant, like 940, something. At that speed, it rotates continuously again. So again, once steady state is arrived, the speed of the motor will be less than rated speed. Clear now? Yes. Okay. So this is transient behavior. Like that, only below rated speeds are possible in armature resistance control. Now let's see what is drawback of this method. Drawback. Drawback of this method. What is the drawback? Above rated speeds are not possible. Only below rated it will give. Above rated speeds are not possible. Okay, next. What is other drawbacks? Due to additional resistance, we are adding some resistance in armature, copper loss will increase here. Due to additional or external resistance, copper loss increases. Copper loss increases. Due to external resistance, copper loss increase. So that's why we don't prefer to reduce very low speed, because if you want to reduce very low speed, you need to add more resistance in that. More resistance means more loss. So more efficient, more power loss means efficiency will be very less. Now, what type of drive it behaves? Below rated. Below rated means constant or variable power. That we need to prove here. See, when resistance added, what is the armature current? V minus EB by RA plus RE. After adding external resistance, denominator increases. Under steady state, as back EMF decrease, V minus EB increase. Approximately current is constant. Denominator increase, numerator also increase. Approximately current constant. If current is constant, torque is proportional to product of flux and current. As it is shunt motor, what is the flux already? Constant. Now what is the current here from the equation? Constant. Overall torque is constant. And what about power? Proportional to 2 pi nt by 60. Proportional to nt. Torque is constant. Now only variable is speed. So these are the variations we need to consider. Power proportional to speed. Whenever speed reduces, power also reduces. So if you draw the graph, torque, power, and speed variation, this is rated speed, above rated, below rated. Previously, we have proved above rated, power is constant, torque is variable. This is for above rated. Previously, we got flux control method. Now, in this method, we are getting power is constant. That is, power is variable linearly proportional to speed. As speed decreasing, power also decreasing. And what about the torque under this? Constant. The torque is constant. This is for below rated speed. Okay, so this graph is valid for induction motor also. Same. So under resistance control, write one point. Under armature resistance control, the motor behaves as constant torque and variable power drive. So you will get questions on like this only. Under constant torque drive, which method is suitable for speed control of DC motor? That is, constant torque drive is below rated. Below rated means either armature resistance control or voltage control also we can use. Remember this. Yes, same. Let's see some questions on resistance control method. Okay, see this question. So I don't do yoga. A 220-volt DC shunt motor operating at a speed of 1440. Okay. The armature resistance is 1 ohm and armature current is 10 amperes. See here, if the excitation of machine is reduced by 10%, excitation means what? Flux. Flux of the machine reduced by 10%. Now what happens to speed? Flux reduced means speed increase. Okay, read now. The extra resistance to be put in armature to maintain same speed and torque means actually when excitation reduce or flux reduce, speed increase. But without increasing that, we need to maintain same speed by adding armature resistance, extra resistance in armature. So how much resistance we need to place so that our speed will be remain same? Okay, simple question. See, draw the figure first. A 220-volt DC shunt motor operating initially at 1440. It is initially running at 1440. 220-volt DC shunt motor. Armature current given directly IA is 1 ampere, 10 amperes. Armature resistance also given 1 ohm, and it is running at N1 equals to 1440 RPM. Okay. Now calculate back EMF under this case. Let EB1 it is. What is back EMF? EB1 equals to 220 minus IA is 10, RA is 1. That is 210 volts. EB1 you will get. Now excitation is reduced by 10%. Extra resistance need in armature. Now we need to add some resistance in the armature. We need to add some resistance in armature like this. Like this, we need to add extra resistance in armature so that the speed of motor remains same as previous. N2 is 1440 RPM. And what happens at the same time? The excitation of the motor is reduced by 10%. How it reduce? We don't require. Reduced by 10% means flux reduced by 10%. Remaining 90% is there. Now calculate again back EMF in this. But IA2, let it is IA1. IA2 unknown for us. Why IA2 I taken? Torque is there in the question. To maintain same speed and torque, so it's constant torque condition. That's why IA1, IA2. How to find? T1 should be equal to T2. Torque in both cases must be same. That's why phi 1 IA1 equals to phi 2 IA2. Phi 1 is what? We don't know how much is that. Let us assume 5. IA1 how much? 10. Now phi 2 how much? Whatever is their flux initially, 10% reduces in that. Means how much will be there remaining? 0.95 will be there into IA2. Calculate IA2 from this. You will get 11.1 ampere. This is the value of IA2. Now IA2 we have, you can find EB2 here. Calculate EB2. 220 minus IA2 is 11.1 into RA is 1 plus RE. That is unknown. We need to calculate RE. Apply the speed relation. Apply the speed relation. N2 by N1 equal to EB2 by EB1, phi 1 by phi 2. Therefore, N2 by N1 equals to EB2 by EB1 into phi 1 by phi 2. What is N2 equals to? What is N2 by N1? 1. Why 1? Same speed, na both cases. 1 it is. Same speed. EB2, just know 220 minus 11.1 into 1 plus R divided by EB1 how much? 210. Phi 1 is let phi 2 is 10% reduced. So in the 5, 10% means reduces means remaining 90% is there. 0.95. 5 cancel. Solve this, you will get the value of RE. How much external resistance it is? Yes. This is 1 point. What is answer? 1.79. Okay. The answer for this is 1.79 ohms. 1.79 ohms. Whatever you will get other option, other answer, that is also will be there like 2.1. Okay. Don't do that mistake. Clear now? The excitation means flux mainly. So that maybe you excitation means flux can be reduced by adding some resistance in the field winding, whatever it is. We don't want that one. See, they said excitation reduced. That's why we reduce the flux. And we should not think again how it reduces excitation like that. Okay. Excitation reduces. That's why flux we reduced. That's it. Next question. Next question. See this question. So this is the question for series motor. Now we have seen shunt. Now it is for series motor. Try to answer this. A DC series motor with a resistance between terminals means total resistance given RA plus RSC 1 ohm. Say a DC series motor resistance between terminals means RA plus RSC both are given combinedly as 1 ohm and it is running at 800 RPM initial from a 200 volt supply by taking a current of 15 amperes. If the speed is to be reduced to 475 RPM from same supply voltage and current, additional resistance in series with armature is dash. See, same supply voltage and current mentioned. How much speed we need to reduce? N2 equal to 475. New speed we need 475. We need to reduce. Same supply voltage 200 volts and also current same 15 amperes. Additional resistance required RE equals to dash. And here RS is Total resistance is given. Okay, what is answer for this? Calculate EB1 in first one. EB1 equals to 200 minus 15 into RA plus RSC. Combination given 1 ohm total, that is 185 volts. Okay, next, adding a resistance, definitely speed will change. Now new back EMF will come EB2. EB2 equals to 200 minus same current 15 into 1 plus RE. This is what is the current in both cases? Same. That's why flux proportional to IA, flux proportional to IA gets cancelled. Same current, same flux. Flux cancelled. Therefore, N2 by N1 equals to EB2 by EB1 into phi 1 by phi 2. What is N2? 475. What is N1? 800. What is EB2 given? EB2 is unknown, RE unknown in this. 200 minus 15 into 1 plus RE. EB1 185. Phi 1, phi 2 cancel. They cancelled because same flux, same current in the field winding. Calculate RE. Only unknown is RE value. How much it is? Yes, 5 ohms approximate. 5 ohms will come. Okay. Next question. This is gate 17, 2 marks question on series motor. Series one. See, this model is different. So before solving this, I will give you another question first. Series question. Write the question first. Write this question. So this question is different model. Up to now, we have seen constant power, constant torque. Now this question is also torque condition, but here I will give some load variation. Load torque proportional to square of the speed, like that. Then based on that, you have to solve this question. Write the question. A 220 volt DC shunt motor draws a current of 22 amperes and running at 1000 rpm. Running at 1000 rpm. Stop. If RSH equals to 100 ohms, RA equals to 0.1 ohm, find external resistance required. External resistance required in armature, in series with armature, in series with armature, to reduce the speed of motor to reduce the speed of motor to 800 rpm. 800 rpm when the load torque proportional to square of the speed, proportional to square of speed. Square of speed. The same as previous questions only, but I given a load torque here. That load torque proportional to square of the speed. So they may give any variation. Load torque proportional to square, load torque proportional to square root of the speed. Any condition they make. Same procedure for everything. Okay, this is another model. See, a 220-volt DC shunt motor initially drawing a current of how much? 22 amps and running at 1000. So draw the figure and find back EMF here. 220-volt DC shunt motor. 220 volts. Running at what is the speed? Running at 1000 RPM. N1 equal to 1000. By drawing a current of how much? IL equals to 22 amperes. And RSH is given 100 ohms. RSH is 100. RA is 0.1. RSH is 100. If it is 100, what is ISH directly? V by RSH. 220 by 100. Nothing but 2.2 amperes. Then what is armature current? IA equals to 19.8 amperes. Armature resistance is 0.1. Calculate back EMF EB1. EB1 equals to 220 minus 19.8 into RA 0.1. What is this value? 2 18.02. Okay, this is EB1. First figure you get. Now what happened? Find external resistance required in series with armature to reduce the speed of motor to 800 when load torque is proportional to square of the speed. So we need to add some resistance in series with armature. So draw the figure first. We need to add some resistance in series with armature. That's it. Voltage is same, 220 volts. How much resistance we should add here so that the speed reduces to 800 RPM. Under what condition? Load torque proportional to square of the speed. Generally, under steady state operation, what is electromagnetic torque and load torque? Both equal. Then only motor will rotate at one constant speed. If one is more, one is less, then there is acceleration or deceleration. But only when both are equal, then only constant speed. That's why under steady state both equal. Electromagnetic torque equal to load torque. In a shunt motor, electromagnetic torque proportional to flux IA. Load torque proportional to square of the speed given. What is the flux in shunt motor? Constant. Remove that. So IA proportional to N square. Using this equation, calculate the current. That's it. Remaining same procedure, same story every time. This is IA1. Now, what is the current IA2? That IA2 we need to calculate. That IA2 we don't know. IA2 we need to find first. How to find that IA2? Using this relation. Use that relation. Use that relation. IA proportional to N square. So, IA2 by IA1 equals to N2 square by N1 square. What is IA2? IA1 is there already here, 19.8. N2 square. What is the new speed they given? 800. 800 square divided by 1000 square. So using this, calculate IA2. What is IA2? Tell me. What is IA2? $12.67, right? Load torque is nothing but, suppose you connected a stationary load. Suppose load means you take any mechanical load, suppose fan load is connected. Fan is attached to the shaft of the motor, some fan. Now fan will have some load torque or not. That is, when you rotate, whenever the load is rotating, whatever the opposition, suppose shaft is rotating clockwise. If you connect a load, actually load nature is stationary. Whatever it is, stationary one previously. Once you connect to the shaft, now that one also should rotate. Now, whatever that rotation is there, at that time, this load is having some torque that is opposing the rotation. That is called load torque. Load torque is provided by load itself. Electromagnetic torque means torque developed in motor it is to drive a particular load. In order to drive a load, the electromagnetic torque should be higher than load torque first. So these conditions you will get clearly in induction motors. If electromagnetic torque is greater than load torque at the time of starting, then only the motor will start rotating under load condition. Suppose if electromagnetic torque is less than load torque, once you given supply to motor will not rotate because load is very high. Load torque is very high. Your electromagnetic torque is very less. Then motor cannot rotate. So these conditions you will get in induction motors. IA2 is 12.67. 12.67. Now same story again. Once you know IA2, find EB2. What is EB2? EB2 equals to 220 minus IA2, 220 minus 12.67 into RA. What is RA? 0.1 plus RE. 0.1 plus RE. RE value we need to calculate. Therefore, N2 by N1 equals to EB2 by EB1 into phi1 by phi2. What is the flux in both cases? Same. Cancel that. Now N2 is 800 RPM, N1 is 1000 RPM. 800 by 1000. EB2 is 220 minus 12.67, 0.1 plus R divided by EB1. What is EB1? 218.02. Calculate RE value. How much it is? 3.5. RE. How much RE? So here T1, T2 we don't use because load torque is given. That's why I said this is another model. Torque constant is then we take same equate T1 equal to T2. But here torque condition given. So we are using that condition. Okay. Yes. The RE value is 3.5 ohms, correct. The value of RE, external resistance required, is 3.5 ohms. Now let's see that question, the previous gate question. That is for series motor. We have solved this one for shunt motor, same as it is this question. First completed this, all of you. Condition we used, that's it. So class maximum 645, 7, not below 7 only, not more than that. See this question. Solve this question same as previous question it is. This is same as previous question, but for series motor it is. Okay, so giving 3 minutes time, try to solve this. So what is the answer for this? Yes, right. Right one. Very good. The answer is 10.7 ohms. 10.7 ohms is the answer. Same as it is previous question, but it is a series motor. That's it. Same as it is previous question. Same condition here. Same condition. See, a 220-volt DC series motor runs drawing a current of 30 amps from supply. A 220-volt DC series motor runs at some speed, because that is not mentioned. You let us assume N1 equal to N, some 1000 RPM or 100 RPM, anything. Okay, N RPM. And its armature resistance is 0.4 and field resistance 0.1. The load torque varies as square of the speed. That is the condition given. Load torque varies as square of the speed. And in case of series motor, as it is series motor, no, what is the magnetic torque of series motor? Proportional to Ia square or not? Flux into Ia. Flux also proportional to Ia square. Now equating both, let us equate both here. Because steady state means both equal. Therefore, Ia square is proportional to N square. As both are square on both sides, let us remove the square. Ia proportional to N. That's it. Now using this relation, to reduce the speed of motor by 50%, the resistance in ohm that should be added in series with armature means we need to add some resistance in series with armature like this. Same supply voltage, 220 volts. We need to find this external resistance. Okay. How much current it is drawing initially? 30 amperes. Let it is Ia1. Ia2 unknown for us. That Ia2 we need to calculate. Ia2 we need to calculate. Find back EMF in first connection. EB1 equals to 220 volts, 30 amperes. Calculate EB1. 220 minus 30 into 0.1 plus 0.4, 0.5 is 15, 205 volts. Next EB2. EB2 is what? Ia2 unknown. First find using this relation Ia2 by Ia1. So directly also Ia2 is what? 15. Why? We need to reduce the speed by half now. If it is N, we need to reduce the speed by 50%. Means new speed N2 equal to half of the previous N by 2. If it is N, it is N by 2. So Ia proportional to speed. If speed is half, current also half. Otherwise, use this Ia2 by Ia1 equal to N2 by N1. So calculate Ia2 is Ia1 30. N2 is N by 2. N1 is N. So N cancel. This is 15 amperes. But directly also you can take. Now EB2 equals to 220 minus Ia2 is 15 into 0.5 plus external resistance Re. EB2 it is. Now apply the relation N2 by N1 equals to, therefore N2 by N1 equals to EB2 by EB1 into 5 1 by 5. What is N2? Half. 50% reduce. N1 is N. EB2 220 minus 15 into 0.5 plus Re divided by EB1 how much? 205 into 5 1 proportional to Ia1. 5 2 proportional to Ia2 because flux proportional to armature current. Ia1 is 30, Ia2 is 15. Ia1 is 30, Ia2 is 15. Calculate NN cancel here. Calculate Re value, you will get 10.75 ohms. This is the answer. Every problem, same procedure, but some conditions will change inside. That's it. There is no variation speak. If speed is reduced by 25%, then N2 value is 0.75 N. 0.75. 25% reduced, remaining is there. Okay, take care of that statements. Is it enough for today? Now voltage control is left in the speed control still. If you wish, we can continue, otherwise we stop. Your wish. Most of you enough. Very few continue. So what to follow? Voting is enough. Ten point 25 or 75 answer. All of you check it once. 10.75 I think. 10.75 only. Yes, right. 10.75 is correct. Okay, thank you. So okay, so most of you wished because of festival and all. Okay, no problem. We will try to complete. Tomorrow we will see the remaining voltage control method, and then we go to braking, and tomorrow itself I will show you starting methods about starter, 3-point starter, how it is started, and some important points you'll see there in the starter. Okay, and whatever is remaining on Sunday we will see. Tomorrow 5:30 to 9:30. Okay, good night all of you. So parallel operation of DC generators we don't have in syllabus. Okay, so if time is there at the last we'll see once, otherwise we leave it. Okay, good night all of you. Yes, okay. Okay, thank you all of you.
Hello, sir.
Tell me.
Sir, before yesterday class, you said, no, sir, under interpoles, the air gap should be more. What is the reason, sir? Can you explain?
Because current in interpole winding is armature current, no?
Yes, sir. Hello?
No.
Hello, sir.
Current in interpole winding is armature current, no?
Yes, sir.
But that is high current. When current is high, the flux produced also very high. Then how to reduce that flux? MMF by reluctance. If you increase the reluctance, we can reduce that flux so that saturation will not take place. For that, we keep more gap there.
Sir, if saturation occurs, then more flux will be there.
Yes, then when there is saturation, the interpoles cannot neutralize the complete armature reaction.
Okay, sir.
That's all.
Sir, slide number 98. If can you please. Sir, here they said the excitation is reduced by 10% now, sir. In question, if it is reduced by 10%, means we have to take terminal voltage, no, sir. Terminal voltage is reduced.
No. Excitation means flux reduced. How flux reduced? ISH equal to V by RSH. Now, field current can be reduced by voltage or by increasing resistance, but it is not given. No, that's why don't take all this. Take only flux variation.
Okay, sir. Okay, sir. Thank you, sir.
Hello, sir.
Till now, this.
Sir, 94 पेज सर. सर इससे पहले वाला. सर इसमें सर एक क्वेश्चन था. एक मिनट को सर, ये दूसरा वाला क्वेश्चन था सर. उसमें ये था कि स्पीड रिड्यूस बाय 475.
यही है.
हाँ सर. हाँ, स्पीड रिड्यूस अगर यहाँ पे सर स्पीड रिड्यूस बाय 475 आएगा तो ये माइनस करना पड़ेगा ना सर.
Yes. Reduced to different, reduced by different. Suppose reduced to बोले तो यहाँ तक.
यहाँ तक.
Reduced by बोले तो ये 800 से निकाल देना.
ठीक है सर, ये था डाउट सर.
Okay.
थैंक यू.
Hello, sir.
Tell me.
Sir, in the armature resistance control method, you are told the transient behavior. Please open this slide. Sir, armature resistance control. Yes, sir, this slide. Sir, here how the electromagnetic torque will achieve the load torque finally?
First, whenever initially both are same.
Yes, sir.
Whenever resistance added, current decrease, electromagnetic torque decrease, then
Yes.
speed decreasing. But whenever speed
Yes.
decrease, again current increase. So again torque
Yes.
increasing, no?
But sir, up to what value the electromagnetic torque increase then?
Up to load torque again.
But sir, the initial value of the load torque is high, na, sir. Then how that electromagnetic torque will again get that load torque value?
Suppose load torque is 10 Newton meters. Electromagnetic torque also 10 Newton meters. Both are steady state at that time.
Yes.
Now, after adding resistor, electromagnetic torque decreases. Let's some 8 Newton meters.
Yes.
2 Newton meter decrease. When it is 8, speed decreasing. When
Yes.
speed starts decreasing, current increases.
Right.
Again, the same torque increases like 9 Newton meter, 9.5, and then 10. It will again achieve 10. Once it is 10, again speed become constant.
Okay, sir.
Okay.
Sir, then speed will decrease, sir, or remains at the rated speed?
No, speed decrease because whenever electromagnetic torque decreases, at that time speed starts decreasing.
Means, sir, our speed decreases, but the torque remains constant. Right?
Yes, torque remains constant.
Okay, sir.
Okay.
Thank you, sir.
Hello, sir.
Tell me, yes.
Sir, I have one general question. Sir, if you're not given any lap or wave winding, what we should take, sir?
Lap.
Lap winding or wave winding, it does not mention anything about that.
Then we cannot take. Actually, it has to mention lap or wave.
Sir, in
Not
our
mention.
bits and bits, there is one question. He's not mentioning anything about the lap or wave winding. He's taken as a wave winding only, sir.
That is wrong. Actually, it has to give. Otherwise, like previously I given one question, current per conductor.
Yes, sir.
At that time, no need of any winding. That depends on question. Otherwise, we cannot solve.
Okay, sir. Means it's compulsory to mention for the finding of the EMF.
Compulsory. Otherwise, if they given in some other way, we have to check it is in the question.
Okay, sir. Sir, one more doubt is there.
Mm.
Sir, he's given as the flux of the yoke. Means flux density of the yoke. He's mentioned that the interior and exterior diameter, sir.
Flux.
Flux density of the yoke is something is given, sir.
Oh.
And the yoke of the external and internal diameter is given 90 and 72.
Internal diameter, external diameter given.
Okay.
Okay.
Sir, how to find that area, sir? Means we should take as a 2 pi r.
2 pi r will give perimeter only, no?
Yes,
circumference. Sir. Surface area you will get, I think. Surface area. If you take internal circle, internal yoke area, internal yoke radius, that is enough, because flux density we have to find internally only, no, not externally.
Yes, sir.
Then internal only you have to take.
Sir, but in this here, finding the height, sir.
Oh.
Height of the yoke and multiply with the interior, yes, sir.
Is not clear. You send the question in the Telegram region. Send it up.
Okay. Sir, your number I don't have them.
Previously given 93928111678 Telegram.
Okay, sir. Sir, one means, sir, if you are taking T proportional to the phi and IA, no, sir. Flux and IA. I confuse in that, sir. That flux is the main flux.
Main flux.
At time I confuse it, it's maybe armature flux.
No, we never take armature flux. Always whatever the flux we are talking, main flux only that is.
For the EMF also, E proportional to
EMF also main flux.
Okay, sir. I will send that question, sir.
Okay.
Thank you so much.
Hello, sir. Chal, Sai Charan Reddy.
Sir, in case of flux control, sir, same that. After listening this armature, I have a confusion in that, sir. Transient.
Okay. Which one?
Flux control, sir. Flux control method, transient period, transient condition.
What confusion in that?
Sir, here we are relating this to the electromagnetic torque and
page number. This one?
Yes, sir.
Yeah.
I'm thinking that both are approximately same, like that.
Yeah, same means what is same? Speed or torque?
So here the torque there the torque remains same and the speed is decreased, but here torque remains same and speed is increased.
Because torque is same only, but speed increases means how it is taking place, because so your doubt I understand. What is that is initially steady state both equal. After that sudden change in the resistance addition, a field current decrease, flux decrease, electromagnetic torque increases. First it is increased. Whenever electromagnetic torque increased, rotor speed will increase or not?
Yes, sir.
Increases. Whenever rotor speed increase, due to that again what happened inside? Back EMF increase. Then what is armature current? Decrease. Again electromagnetic torque decreasing. So it will reach again up to low torque. Again it reaches constant speed. Now your doubt is again torque reaches to same value means how speed increase. That is the nature of motors, no? Depends on relation between electromagnetic torque and load torque. So automatically speeds will change based on the two. If one is increased, one is decreased, speeds will oscillate there. Suppose load torque increases suddenly. Some load additionally added, load torque increase, then speed of motor decrease. Again, it comes back to steady state operation. Speed will increase again? No. Speed will be remain same only, decreases. So no, don't confuse. Just follow these statements enough.
Okay, sir. Here, is this a reason for inertia, sir? You are saying that it's a
Yes,
nature
yes, yes, yes.
inertia.
Due to that inertia only transient is there. Otherwise, instantly speeds will change. No.
Okay, sir. Sir, in one case, you told that we should not directly take the torque relation for the speed finding, sir. In which cases it is possible, sir? I did not understand that statement, sir.
It's where it is.
Sir, yesterday, day before yesterday, you said in a problem that we should not take directly the torque equation for the finding of speed.
Finding of.
Speed, sir, speed.
I forgot where it is.
So, it's not today, sir. Day before
Which
yesterday.
topic name?
Topic. Sir, in that motors only, sir. Motors. The types of motors, sir.
I think suddenly field winding shorted are there only. No?
Yes, sir. Yes, sir.
There torque proportional to flux IA. In that case, first we have to check current IA is 0 or not.
Okay.
Okay, current IA is 0 or not. If current IA is 0, definitely motor comes to stop. But if IA is there, then you have to check without with respect to flux. What is the flux variation? So there I given some equations, not directly for every question. If shunt field is open circuited or short circuited, what happens? So you check one time again the figures.
Okay, sir.
Okay.
Okay, sir. Thank you.
Okay.
Sir, good evening, sir.
Tell. Please.
Sir, at 77. Sir, here, why don't we get ID as constant? Sorry, I armature current.
IA constant means, suppose IA
Yes, sir.
constant.
ID increases and ISC decreases.
Okay,
right?
IA
So why don't-
constant, IA constant. In that ID increase, ISC decrease. Okay.
Yes, sir.
If ISC decrease, what is the flux? Decrease.
Decreases.
Now flux decrease means, let us consider in the torque equation, flux only decrease.
Okay, sir.
Then what happens?
The
Current
torque
same.
decreases. Okay,
Then
sir.
torque decrease, no?
Yes, sir.
And then how torque will be remain same? If IA increase.
Okay.
Okay.
Yes, sir. So then 93. Sir, here the same excitation thing, sir. So it is reduced by 10% means we should consider voltage or flux.
So excitation means mainly flux we have to consider, not voltage. Because if you change voltage here, this EB we have to change again.
Yes,
So
okay.
we don't require all this. How excitation they changed in the question given excitation. That's why flux directly we reduced. So they may reduce by adding resistance. This is not given.
Okay, sir. For
Okay.
like any problem, we should consider. Suppose if excitation means like
flux directly.
Okay. So then 97 is
90.
97. Sir, here could you explain that IA proportional to n square relation one more time?
IA.
IA proportional to n square relation. How you got that?
Oh. Because load torque proportional to n square given.
Okay, sir.
And electromagnetic torque of shunt motor proportional to flux IA, but flux constant in shunt motor only IA. Under steady state both equal. That is IA proportional to n square.
Okay, by equating those two statements, we got
yes.
IA proportional.
Yes.
Yes, sir. That's it. Thank you.
Pratyush, tell me. Hello, Pratyush. Hello. Not audible.
Hello, sir.
Tell me.
Sir, in case of field flux control, you have said that the speed changes, but the electromagnetic torque remains same, sir.
Which one?
Sir, in case of field flux control, sir.
Mm-hmm.
Hello, sir.
Tell me. Field flux control.
Sir, is it audible, sir?
Tell me.
Yes, sir. Sir, in case of field flux control, you have said that the speed changes, but the electromagnetic torque remains same, sir. But the power is nothing but torque into omega, but the power is constant, sir. How it is, sir? Constant power drive.
Power is proportional to N
Torque
into T.
Is here torque constant, but speed changes, sir? Then how it is a constant power drive, sir?
That is with respect to only flux we are talking again. So you should not compare this one with the power equation. So there only flux IA, but whenever flux decrease, I did not consider IA at that time.
Yes, sir.
Because with only one variable, what happens, speed and torque, we are verifying. That's it. Okay.
Okay,
Don't
sir.
compare that IA with this one. Then it will change, how it is satisfied.
Okay, so then there will be change in torque, no, sir? Then.
Yes, definitely changes.
Yeah, okay, sir. Sir, another one, sir. You have said that in yesterday's class, in case of series generator, we have high full load voltage, sir.
High full load voltage.
Sir, but in case of our compound, even though the fluxes are riding, we have two fluxes, but we are not getting that much full load voltage, sir. Why, sir?
So full load. See, in the figure, I taken full load voltage of series generator is highest. Actually,
Yes,
it is not like highest always. Compound also make it highest. Just I drawn a graph, so it came like that. It is above the over compound. It is not like always. It is series is greater. Over compound also make greater than series. It is not fixed like that.
Okay, sir. Sir, general doubt, sir. Sir, you have said that there are three drives like power drive and torque drive and change one another drive, sir. Sir, how the car is modeled, sir?
That is completely different, no? And that is IC engines.
Sir, normal EV, sir. EV it tells, sir. No?
I don't have idea of that. Which electric cars you are talking?
Yes, sir.
No idea.
Okay, sir.
Sir,
can you tell the exact difference between the speed and torque, sir?
Speed means rotational. That is rotation. Speed means torque means which drives the rotor.
Okay, sir. Means torque is not. We should not think like torque is nothing but the rotational force to move an object, sir.
Rotational force only.
So then that means if we increase the rotational force, then the speed of object should be increased all the time, no, sir? Means, but we are not saying always the torque is directly proportional to speed, no, sir?
That depends on nature of motors. No, every motor is not having same nature. If you take series motor, no load condition, what is the speed of series motor? Dangerous high speed. That means his torque is very high at that time.
Yes, sir.
No.
Okay, sir.
Torque is very less. Still, it is running at dangerous high speed. That is the nature of motor. Okay, even sir, at low torque, that small torque will make the rotor to rotate at high speed.
Okay, sir. Sir, okay, sir. So the last one, in case of shunt generator, we have normal terminal voltage drop due to armature resistance, and due to armature reaction, we have drop. And sir, is this drop is same as that one, sir? That means due to voltage drops, terminal voltage drops, we have again the shunt current
Yes,
drop.
yes,
And
yes.
sir, there are 3 drops or only 2, sir?
3 drops. 3 drops will be there in shunt.
Okay, sir.
Armature resistance drop plus brush drop. Again, when voltage drops, again field current little drops, again voltage drops.
Oh,
But it
okay,
is not there in separately excited.
okay, yes, sir. Yes, sir. Yes, it is a flux voltage constant.
Yes.
Okay, sir. That's it, sir. Thank you, sir.
Okay.